Okay, sir, we'll start within 1 minute, sir. No problem. We are starting.
Okay, good afternoon.
Also, sir, can I start now?
Sir, let me know that how many participants from abroad. Do you have any some statistics about this?
Yes, yes. Most of the participants who are admitted in this will be from abroad, sir.
How many? Do you have any figures?
Now in the Zoom, sir, or in registration?
Oh, in registration, I am talking
In
about.
registration, almost, sir, near about 400 registration are from abroad, sir.
400. And from which countries?
Consider Mexico, Philippines, Nigeria, South Africa, sir.
Okay.
Also
Very
from okay, 4 or 5 countries are there, sir. Mexico, Philippines, Indonesia is also. Indonesia, then Nigeria, South Africa, sir. Slovenia is also there, sir. Slovenia.
Start.
Okay, sir. Thank you. Sir, total registration near about 2,500 approximately, sir.
Very good.
Okay, sir. Total registration near about 2,500 approximately, sir.
Very good.
Repetition. We'll start in 1 minute, sir. Okay, sir, we are admitting a few people from here, sir. Just wait for 2 minutes. Sir. Also, sir.
Yeah.
Can I start, sir?
Yeah.
Okay, sir.
Please start.
आवाज आ रहा बीच में देखो.
Unmute कर दो.
Okay, good morning. Good morning to all the participants. Okay, good morning. Good morning and very warm welcomes to one and all excellencies, delegates and dear participants. I am Dr. Satish Kola. Welcome you all for the one-day international e-conference on multifunctional advanced material, that is ICMAM 2020, organized by MG Art Science and late NP Commerce College, Armory. Encouragement, enthusiasm, and excellency is one of the major aspects of our organization, with an object of encouraging the spirit of research and innovation. Today, our institution arranged this conference. For this conference, we are having four eminent personalities from different areas of the world. It's my immense pleasure to give a brief introduction about these eminent personalities. Actually, this is a very rare chance to get opportunity to listen in a one platform to these wonderful persons. It's my privilege to introduce the first resource person, speaker, Dr. Pankaj Koinkar, Associate Professor, Department of Optical Science, Fukushima University, Japan. The second research person is Dr. D.W. Kurnulisar, Associate Professor, Kamla Nehru College, Nagpur, Maharashtra. Third research person, Dr. Dr. David O. Ubada, Department of Mechanical Engineering, Amatu, Bello University, Zaria, Nigeria. And fourth eminent person is Dr. B.P. Kafle, Associate Professor, Department of Chemical and Engineering, Kathmandu University from Nepal. I heartily welcome all the eminent personalities for this international e-conference. Now, it will be my honor, I request my Principal of Organizing Institution, Dr. Lal Singh Khalsa sir, for opening remarks and inaugural speech. Dr. Lal Singh Khalsa sir.
A very good morning to you all. It's my great pleasure to welcome you all to this one-day international conference on multifunctional advanced material organized by the Department of Chemistry of our college. Respected dignitaries, among the eminent speakers, Dr. Pankaj Koinkar, who is from Fukushima University, Japan, Dr. W.B. Kurnulisar, he is our friend from Kamla Nehru College, Nagpur, Dr. D.O. Obada, he is Ahmadu Bello University, Nigeria, Dr. D.P. Kafle from Kathmandu University, Nepal, respected principal of the various colleges, faculties, researchers across the India and the globe. I am glad to share with you all that as of now, we have total 2,568 registered participants among with us. But among them, we could allow only 100 participants on Zoom platform, while rest of them, about 2,068 participants, are living on live YouTube stream live. This large number of registered participants across the world shows that the need and importance of this particular theme of e-conference. I am the principal, Dr. Lal Singh Khalsa, Mahatma Gandhi Art Science and Late NP Commerce College, Armory, which is located in the one of the remote and tribal area of the Maharashtra state of India. And our college is catering the higher education under the flagship of Manor Bhai Shikshan Prasarak Mandal, which is our education society, since 1981, for various programs and courses at UG and PG level, including the Masters in Chemistry, various skill-based, job-oriented courses, community colleges, and higher and learning research center in the various subjects in these particular rural and tribal areas. Our college is, I am very proud to share with you that our college is accredited by NAC A grade. It clearly indicates that how much we are concerned about the quality and holistic education. While I am talking about today's e-conference, the prime purpose or prime aim to organize this particular one-day international e-conference on multifunctional advanced material is to provide a platform where the resource persons, researchers can come together, stand together, discuss together, and proclaim the knowledge and share their new ideas from the research areas of material science, nanotechnology, chemistry, physics, and indulge in the interactive session at this particular event. Of course, we everybody knows that materials by themselves do nothing. Yet without materials, man can do nothing. Materials plays a very significant role in the life of the human being. As the advance of the human civilization, we know that the advancement of the human civilization is fully depend on the materials of the evaluation. As we remember our old civilizations, Stone Age, Bronze Age, then Iron Age, Silicon Age, cities with steel, then aluminium, plastic, ITs, green technologies, and now just composite materials. We are talking about composite materials, hard materials, piezoelectric materials, electroactive polymers, biocompound fibers, and there are various types of smart materials now we are using, and the using of these types of materials are very extensive use of materials by us in day-to-day life. In fact, I say that all the spheres of our life is greatly influenced by these materials. So thus the themes of this e-conference is definitely very thought-provoking, and hope that we will all enjoy this e-conference and indulge in interactive sessions and make this conference scientific. At the last, I congratulate organizing committee for organizing such a great event, and also thankful to our management, particularly for our president, for monitoring and motivating, cooperating to organize this wonderful event, international conference. And here I declare in the last the inauguration of this conference. Thank you very much. Over to Poonam.
Okay, thank you so much, sir. Thank you, sir. It's always inspiring. Your words are always inspiring us, sir. Thank you. Thanks a lot. Now I have request convener, Professor S.M. Sontake, sir, to give brief introduction about the first speaker, Dr. Pankaj Koinkar, and start our first session, sir. Professor S.M. Sontake.
Thank you, Satish. I'd welcome four eminent researchers, Dr. Koinkar sir from Japan, Dr. Gunule sir from India, Dr. Obada of Nigeria, and Dr. Kafle of Nepal, and all the participants across the globe for today's international e-conference on multifunction advanced material organized by Department of Chemistry of Mahatma Gandhi College, Armori. Currently, entire world is struggling against viral pandemic COVID-19. Today we are witnessing unbounded global spread of the disease. Unfortunately, each of us is affected. But as we know that after every winter there is summer. In the same manner, life will become normal after this COVID-19 pandemic. Today, we are in the era of science and technology, and we know that material science is the interdisciplinary field involving properties of matters and its application to various areas of science and engineering. Material science and engineering is a key aspect of most of the companies of the world. There is always a race for companies to make stronger, cheaper, lighter, more advanced, and sustainable materials to produce. Scientists and researchers play key role in development of advanced material. Multifunctional advanced material are the materials that perform multiple functions in the system due to their specific properties. Multifunctional material can be both naturally existing and specially engineered. Main objective to organize e-conference is to communicate, sharing the ideas of all the academia, researchers, industrialists across the globe. Let me introduce today's keynote speaker, Dr. Pankaj Goenka sir, presently working as Associate Professor at the Department of Optical Science, Tokushima University, Tokushima, Japan. Dr. Pankaj Goenka started his research career as JRF at the Department of Physics and received his PhD in 2005 from North Maharashtra University, India. He worked as research associate in the University of Pune for a few months in 2005 and subsequently went to Korea University, Seoul, South Korea for the postdoctoral study in 2006. After 1 year postdoctoral study in South Korea, he joined the Center for International Cooperation in Engineering Education, the University of Tokushima, Japan in March 2007. He became an associate professor in the Department of Optical Science, Tokushima University in April 2016. He is also working as Vice Director of Center for International Research and Education Collaboration in Tokushima University. Dr. Pankaj Goenka research area includes 2D nanostructure, conducting polymer, laser ablation in liquid, field emission spectroscopy, and engineering education. He has published more than 80 research papers in peer-reviewed international journals and got 2 awards for paper presentation in international conference. He has been working as a reviewer for more than 100 SCI journals from elsewhere, that is Holland, Springer, Germany, American Chemical Society, United States, World Scientific Publication, Singapore. I am really fortunate such a brilliant personality is with us. Therefore, I invite Dr. Pankaj Goenka sir to communicate his expertise with us. Dr. Goenka sir, please.
Can you hear me? Am I audible?
Yes, sir, you're audible. Yes, sir, you're audible. You can start.
Thank you, Professor Sontakke, for introducing me. Good morning to Dr. Khalsa, all respected speaker and all respected audience participants. Today, I am going to share my experience on nanomaterial, basically two-dimensional nanomaterial that we have prepared using the laser ablation technique and what kind of application these material have. The outline of my talk is having 5 different aspects. First, I will give brief introduction of Tokushima University, and then I will move to the two-dimensional material. After that, I will explain what is the laser ablation process, and then I will give some examples how we have synthesized the various kind of nanostructures using laser ablation process. Finally, I will talk about the ongoing research, we are working on various kind of two-dimensional nanomaterials. So that will be my last topic in this talk. So first, I will move to the Tokushima University. As you heard that I'm working in Tokushima University. I'm working in Tokushima University from last 14 years, almost 14 years. The Tokushima is located in one of the small island in the south part of Japan. So you can see this is the small island called as Shikoku. It has 4 different cities: Kagawa, Tokushima, Kochi, and Ehime. So Tokushima University is located in Tokushima city. This is the location of Tokushima in the map of Japan. The nearest airport is Kansai International. It is 180 kilometers from Tokushima. So this Kansai International Airport is built, is a man-made international airport in the sea. So it's a very beautiful airport. If you have a chance, please visit Tokushima, and also you can able to see the Kansai International Airport. It's a very beautiful airport. This is the pictures of our campus. We have basically 2 major campus and 1 administrative office. Kuramoto campus is belong to the medical faculty, faculty of medicine, pharmacy, dentist, and so on. While Josanjima campus is mostly for the engineering faculty. And we have 3rd administrative head office at Shinkura. So these are the 3 different campus. They are located 2 kilometers from each other in the Tokushima city. So in department, in the faculty of engineering, we have 7 departments: civil engineering, mechanical, chemical, biological, electrical information, and optical system engineering. I belong to optical system engineering. Under this 7 department, we are giving the bachelor and master's degree as well as doctoral degree in 3 different subjects like intelligent structure mechanics and life material system and system innovation engineering. In Tokushima University, including medical campus and engineering campus, we have about 956 teachers, and there are 9,000 students. They are studying now. Out of these 9,000 students, we have 638 international students from different countries, different parts of the world. And we have 1,400 office staff. We have various international collaboration in order to enhance the joint activity between these partner university to promote the student exchange as well as faculty exchange. There are 27 countries who are associated with Tokushima University, and 92 university has signed MOU with us. Most of the university is from Asia. You can see there are 65 university, and then a few from Europe and North America also. These are the pictures of faculty of engineering. This is the aerial picture you can see. And I'm sitting in this building now. This building is the optical science, same as here, I'm sitting here. So this is aerial view. This is the main head office of Faculty of Engineering. And these are various department, various building in which various department are working. Now coming to my today's topic, that is two-dimensional material. You might have seen these pictures. These are 2 gentlemen, those who got the Nobel Prize for their groundbreaking research in the field of graphene. In 2010, they received Nobel Prize for creating the graphene in the laboratory. Actually, in 2004, they have created the graphene and they started to work on the electrical property of graphene. And after 6 years, they received the Nobel Prize because graphene is a unique material and it has excellent property for optoelectronic devices. So for their contribution in the field of making graphene, they received Nobel Prize in 2010. So most of us who are working on the material, they know about these two gentlemen, Andrejim and Nevesolov. So what is graphene? Graphene is a single atomic sheet of graphite. So can you see the graphene? We cannot see by our eyes because the graphene is in nanometer and our eyes cannot catch anything which is on the scale of nano. But you can do the experiment. Whenever you are rubbing the pencil on any kind of plain paper, you are creating thousands of layer of single graphite. So single sheet is nothing but a graphene. So whenever you rub pencil, make sure that you are creating graphene, but you cannot see the graphene. You need some kind of microscope to see the graphene. So this is the naturally, you can see the existence of graphene. But laboratory on this, in the laboratory, when you want to prepare the graphene, there are various technique, chemical, physical, where you can prepare graphene-like structures. So graphene is a single atomic sheet of graphite. If these single sheet is attached to each other, then it becomes graphite. But if this single sheet is laying independently, that is graphene. So there is a difference between graphite and graphene. You can create the graphene from graphite. There are various two-dimensional material like graphene, graphene, boron nitride, molybdenum sulfide, tungsten sulfide, and so on. So these are some of the example of 2D material, including graphene. Since the Nobel Prize has received in 2010, and now we are in 2020, so 10 years. Within these 10 years, there are thousands of papers published on the graphene. Most of the properties of graphene has been revealed, and some of the commercial application of graphene has been also seen in some reported data. But scientists want to create a similar kind of material which has a property like graphene. So they are looking for different kind of material which is two-dimensional material, for example, molybdenum sulfide or tungsten sulfide and so on. So this is the family of you can say two-dimensional material, but make sure that a new type of material, graphene and graphene. These are two different material. Recently, there are some report on the graphene as well. So difference between graphene and graphene is the sp2 and sp3 configuration. Same like when you talk about the diamond and graphite. So there is a sp2 and sp3. So diamond is pure insulator, but graphite is not insulator. So why researchers are interested in two-dimensional nanomaterials? So first material is the graphene. Now in case of graphene, you can see how the carbon atom is attached to each other, how they are making bond with each other. So as I explain you, the graphene is nothing but it is made up of carbon atom. There are carbon atom everywhere. So one ring, hexagonal ring, has 6 carbon atom, and then that ring expands horizontally, that is graphene sheet. And this is two-dimensional material, and it conducts good electricity because energy band gap is 0. So that is the special property of graphene. Then molybdenum sulfide, molybdenum atom is shown in yellow color here, and sulfur is shown in blue color. So they can make such kind of expansion of molybdenum and sulfur atom and create a single sheet of molybdenum sulfide. It is two-dimensional material, of course, and it can also conduct the electricity. But this is a kind of semiconductor, not exactly like graphene, because graphene has a 0 energy band gap. While boron nitride has similar kind of structure. If you look at graphene and boron nitride, what is the difference? The boron nitride has boron and nitrogen atom. So boron is shown by yellow color, while nitrogen is shown by purple color in this structure. Despite they have a similar structure, what is the difference? The difference is located in the conductivity. The graphene is good conductor, but boron nitride is a kind of insulator. But it has a good thermal resistive property. So graphene has certain property that can be used for various applications, while boron nitride can be used for different purposes. That's why we are interested in graphene, we are interested in molybdenum sulfide, or we are interested in boron nitride. In last 10 years, there are several reports has been published on the two-dimensional nanomaterial, right from the synthesis to the large scale synthesis, exfoliation, various kind of physical, chemical methods, technique has been shown to prepare the two-dimensional material, for example, molybdenum sulfide, tungsten sulfide, boron nitride, and so on. And their optoelectrical property like field effect transistor for display purpose and various other property has been revealed by many scientists all over the world in last 10 years. Now, what is a laser ablation? Since we are preparing the two-dimensional material using the laser ablation. So what is laser ablation? In case of laser ablation, we use a laser. When we use the laser, that laser energy has been utilized, has been used to remove the material from the target. So laser energy can be useful aspect to remove the surface part of any bulk material, target material. So this high power laser pulse hit the surface of target material, and it can, there are various kind of physical process happen like melting, evaporation, ionization, and removal of material, depending on what kind of bulk material and how much laser energy we are using, how much laser ablation time is there. So there are various parameters which decide what kind of physical process will occur during the laser ablation. We are using nanosecond and femtosecond. Beside this, you can use microsecond, picosecond laser also. And using this laser ablation process, we can prepare oxide, metallic, fluorine-like, carbide, nitride material. The size of nanostructure varies from 5 nanometer to 100 nanometer. So you can prepare the nanostructure up to 5 nanometer and maybe 100 or 200 nanometers. So this is a explanation of laser ablation process. There are various laser, as I explained you, continuous laser. So what is continuous laser? When you give any kind of presentation, usually you use a laser pointer. So when you on the laser point, the laser is continuously on. It is not like on off, on off. So that is a kind of continuous laser. Once you on the laser rays are coming continuously without stopping. So that is called as continuous wavelength laser. So CW laser. It can hit the target material and damage this much material or in order to remove the surface part of bulk material. But in case of nanosecond laser, since nanosecond laser is a pulse laser and it has a pulse of 10 nanosecond with certain energy, in our case, it is 50 millijoule or you can say 500 milliwatt. When you irradiate the bulk material using the laser, every time there is a pulse of 10 nanosecond. So this pulse is going on the surface of bulk material. So it can create some kind of plasma at the surface of the material, and it can affect the certain part of bulk material because it has certain energy and it can be having a certain pulse rate also. But since the power of these nanosecond laser is about 500 milliwatt, after hitting the bulk material, it also create a shock wave. Shock wave means when you put any kind of stone into the river, it create a circular rings, various circular rings started from the center. So those kind of waves are also created by the nanosecond laser. Recently, you might heard about the bomb blast, or you can say the explosion of ammonium nitrate in Beirut. So when explosion occurs, it creates a shock wave, and most of the window in the apartment, even from 1 or 2 kilometers, has been broken. So that was a kind of shock wave created by the explosion. Similarly, this nanosecond also create a kind of shock wave, and it goes deep into the surface of target material. In case of pico or femtosecond laser, the power of this laser is less, like 3, 5, or 6 milliwatt. So it can maybe affect a small part of bulk material, and it create a shock wave, but the area is very less as compared to nanosecond. So when the nanosecond laser is used, why we called it as a nanosecond laser? As I told you that nanosecond laser is a pulse time. Laser has one pulse is about 10 to the power minus 9 seconds. So when this pulse of laser is hitting the target material, and we are using the liquid medium, like this. When we irradiate any kind of bulk sample using the laser, here this bulk material, this target material has been put into the liquid. Now, when this laser is hitting the surface of these bulk material particles, it creates a plasma. And this is the solid material, the black, you can see the solid material. And when it hit the material, because of the laser energy, it also create removal. It can remove some part of the bulk material. So while removing, there is vaporization also occurs. And as I told you that in this process, this red ring shows the shock wave. So shock wave is also created inside the bulk and also down to the target material. So this is the physical phenomenon occurs during the laser ablation. And now I will explain the synthesis. We have synthesized indium selenide nanocubes using this process where we have used indium selenide powder as a bulk material, and we irradiate using Nd:YAG nanosecond laser having the wavelength of 532 nanometer, and its pulse is 10 nanosecond. The power is 50 millijoule. The size of the beam is 5 mm. The laser beam size, I'm talking about the diameter of this laser, is 5 mm. And we irradiate for about 20 minutes. Then after irradiation, what we have seen, this is the bulk material you can see in figure A. The two-dimensional material is a kind of sheet. They are attached to each other, or they are laying on one on another. So such kind of layer material is used as a bulk material. So you can see there are several layers of indium selenide material in the bulk. But after laser ablation for 20 minutes, so indium powder, and this is the water, simple water, deionized water we have taken. This sheet material is totally transformed into the cube. So this is ACM image, you can see some cube, and this is a TM image. So the bulk material, and this is the cube. So you can see these are the cubes. And we have confirmed through EDAX whether there is indium and selenide still present. So why these sheets has been transformed into the cube? The irradiation time or laser ablation time was 20 minutes. So what happened during this 20 minutes? First 5 minutes, you can see when the laser time, when the ablation time is only for 5 minutes, we prepare one sample and took his ACM. So we have seen there are some kind of rod-like structure and some spherical particle also there. After 10 minutes, we prepare another sample and took ACM. Now these big rods are still there and some circular particle are also present. After 15 minutes, now you can see the formation of cube has just started, and there are some sheet also present after 15 minutes. But after 30 minutes, after 20 minutes, the total material has been converted, or you can say transformed into the cube. We have also taken the ACM of 30 minutes. I have not shown here, but after 30 minutes, the cube become amorphous. So 20 minutes is the best time to get the nanocube. That's why I have not shown you the ACM of 30 minutes. So after 20 minutes, you can see these structures can be totally converted into the cube. We started with the bulk material and ends with the cube material. We have seen it's a field electron emission, that is optoelectronic property. Whether this material can be used for display device, that is field emission display device. We have observed that this material can produce the current density up to 2.5 microampere at 9.7 volt per micrometer. So this much electric field required to get the current density, to draw the current density from these nanocube. This is a kind of high current density we are getting as compared to other available material. Then why these material producing high current density? Because of two reasons. One reason, it's having the nanometric surface morphology, and once this material goes into the nanometric surface morphology, it can also enhance the electrical property, because as compared to bulk material, the bulk material is just giving the electric current density up to 400, somewhere here it is giving the current density. So 400 to 2.5 microamp. The current increases almost 6 times as compared to the bulk material. So it shows that the improvement in the electrical conductivity also, and that might be one of the reasons to enhance the field emission property. We have also seen the current stability, because when we talk about the display devices, you need the stability of any kind of devices, whether the material is really stable or not. When you are going to apply a high voltage, the current will be stable or not. If it is not stable, then you are not going to prepare the good devices. That's why the current stability is one of the important factor, and it is almost stable. The current is almost stable after 5 hours. The next material we have prepared is the bismuth selenide. You can see this is the bulk material, and we crush for 2 hours in IPA, isopropyl alcohol, to make the fine powder. And then this is the fine powder we put into the bottle. You can see the color of the powder is black. Before the laser ablation, you can see the black color, or you can light gray. After laser ablation, this color is changed into yellowish brown. That is the one of the characteristics, or you can say the sign whether the nanostructure has been formed or not. Visually, it's give the sign if the color is changed. So this is the bulk material, and this is the laser ablated. After 2-hour ablation, you can see these are sheet. Since we crushed the sample, this was the bulk sample, and after crushing, but in case of bulk sample, there are some small particle and there are some big. But when we started to crush, the smaller particle become more smaller, and maybe these bigger particle still remain a sheet of 1 to 2 micrometer or several micrometer in the size. But there are some sheets of 500 nanometers, you can see, since the bulk material is not uniform. But after laser ablation, you can see the rod-like formation occur in case of bismuth selenide material. We have again seen the field emission property. It also improve, but not improves much, because 400 to 600 as compared to this indium selenide, where you are getting 2.5 microampere current density. Here you can see only 6.5, 647 microampere. Here it was, sorry, 2500 micrometers. So that is 2.5 milliampere. And third sample we have prepared is molybdenum sulfide nanosheet. The irradiation time was 20 minutes and 120 minutes. We have seen the laser ablated sample. We characterize using Raman spectra and several other like XRD. This is the published paper in 2018. And here also, when you compare the bulk sample, you will find after 2 hours of laser ablation, nanosheet of 200 or some 100 nanometer has been created. This nanosheet can also increase the current density. After formation of nanosheet, as compared to the bulk material, there is an increase in the field emission property. Why this increase occur? There are two different reasons. Of course, one reason is the nanometric scale. Other reason is removal of MOO3. So when you look at the Raman spectra, there are MOO3 peaks are there, 1, 2, 3, and 4. But after laser ablation, this intensity of this peak is reducing. It might give the sign of removal of MOO3 particle present in the bulk material. So there are two different reasons for this. And beside this, we are working on several other material like bismuth sulfide, and also working on molybdenum sulfide, indium selenide, and tungsten sulfide using the nanosecond laser and femtosecond laser. You can see change in the color. And when we are working on the bismuth selenide material using femto laser and nanosecond laser, we have vary the solvent. We use different kind of solvent. For example, water, isopropyl alcohol, methanol, ethanol, DMF, hexane. So we are getting the different surface morphology of bismuth selenide material, nanoparticle, nanosheet, nanorope, or nanocube, nanotube, nanorope. This study is under investigation, and we need to explain why this growth mechanism, why this kind of structure is formed after the laser ablation. So we have to propose some growth mechanism for this material. And a promising application of these two-dimensional nanomaterial lies in the photonics energy or solar cell or light emitting diode or flexible display devices or for energy harshening as well as for the sensor. So these material has wide scale of application. That's why most of the researchers all over the world are working on two-dimensional nanostructures. And in future, we want to develop two-dimensional material which can be used for various emerging application, especially in the field of optoelectronic devices. Finally, I would like to thank my collaborators and group leader, Professor Furube, and collaborator from Japan, Moriga, from Taiwan, Professor Lin, from India, Professor More and Shirsat, and my graduate student. These are 1 to 5 master student and one of the doctoral student who has created this material, and so that I can able to share my experience based on their work they have done. So thank you very much, and I will be happy to give the answer if there is any question based on my talk. Thank you very much.
Okay, sir. Thank you. Some questions are there in chat box, sir. Okay, I will discuss, sir, one by one. Okay.
Okay.
Liz Mary Anthony from Kerala is discussing one question. Is there any advantage or disadvantage for the sharp wave produced due to nanosecond laser hitting on the bulk material?
Is there any advantage on what?
Or disadvantage? Is there any advantage or disadvantage for the shock wave produced due to nanosecond laser hitting on the bulk material?
There is an advantage, like shock wave can reach more deeper surface of the target material. So the process of formation is more faster than the femtosecond, because laser is reaching to more maybe deeper as compared to femto laser second. So the laser nanosecond laser ablation is a fast process. Another disadvantage is that since it is a liquid medium, it cannot create the impurity. It cannot create the impurity. We are getting the pure form of nanostructures after the laser ablation. So this is eco-friendly kind of technique, and there is no possibility of impurity formation during laser ablation. Is it okay?
Okay, sir. Okay, fine. Another question is there, sir.
Yes, yes.
How nanoscience can be used to pollution control?
Yeah, there are. There are nanoparticle that can be used for controlling the pollution. You can clean the water using some kind of nano material, or you can prepare some kind of filter based on the nano material, or you can prepare some sensor that can at least control the pollution level. It cannot, you can say, reduce the level, but sensor can control the pollution level. So there are various nanostructure that can use for pollution control. I'm working in the field of optoelectronics, so pollution is not my major, but I have read some article that there are some kind of nanostructure those can be used for maybe pollution control in the field of biology, or even in the field of chemistry for gases, or some filtering or cleaning of water. And there are several other applications also.
Okay, thank you, sir. Thank you so much. Thank you, sir. I will move on to
Okay.
Questions are over, sir. Thank you. Thanks a lot.
Okay, thank you. Okay. Thank you very much.
Thank you so much for your great knowledge you have shared with us. It's a spectacular knowledge about the laser technology. We definitely take the advantage. The participant will definitely take the advantage of it. It's our great pleasure once again to hear in future also, sir. Thank you so much for joining us, sir. Thanks a lot. Now I will move towards the next speaker of this conference, Professor Dr. Gurnuli, sir. It's my immense pleasure to introduce D.W. Gurnule sir. Gurnule sir is working as an associate professor in Kamla Nehru College, Nagpur, Maharashtra. He has published many articles and he has worked on nanomaterials since 10 years. He has received CSR Best Teacher Award in 2011 for outstanding contribution in polymer material. He has also presented Chemicals Research Society of India in Bangalore. He has also received Distinguished Scientist Award in 2016 for their contribution in research work at Chennai by the Center of Advanced Research. He has also been received ABBA International Outstanding Researcher Award in 2016 by ACS Publication. His academic achievement includes Best Research Paper Representation Award for 6 research papers in conferences. He has published more than 360 science articles in daily newspapers for the Peoples of Society aim to publish more than Peoples of Society aim to popularize the science. He has successfully guided 22 students for PhD degree and 6 are currently registered for PhD. He has successfully guided 21 MPhil students for their dissertation work and he has successfully completed 3 research projects. He has published 32 books, 4 chapters, 4 of which were international level publications by Apple Academic Press in Canada. He is the Secretary of Society for the Promotion of Material Science. He is the Secretary of West Zone of Association of Chemistry Teacher. So it's a big and long biodata there. I'll give a brief introduction about Dr. W.B. Gurnule. It's an immense pleasure to listen about the knowledge of W.B. Gurnule sir. W. Gurnule sir, you can start your presentation.
Okay, thank you. I'm audible?
Yes, sir, you're audible.
Okay, thank you for your kind introduction. And first of all, I thanks the organizer for inviting me for this international e-conference on multifunctional advanced material organized by Mahatma Gandhi College, Armory. I would like to thank the principal of the MG College, Armory, Dr. Lal Singh Khalsa sir. And I also would like to thank the convener, Professor Sontake sir, for organization and for inviting me for such a great event of international multifunctional advanced material. And dear participants from the globe and from the country. The topic of today's presentation is the multifunctional material and its impact on the society. This talk will be useful to all the teachers, also youngster, researcher, and students also. So here I'm giving some that is the introduction and also some applications of this material, how the material works and how it is useful to the country and also to the society. So this is the building of my college, Kamla Nehru Mahavidyalaya, Nagpur, located in the Sakkadera Square in the east part of this Nagpur. And before going to start the presentation on the material, see here some human values are there, and there are 12 human values, that is non-violence, humanity, honesty, all these, the one person should have all these 12 values of human. And as we know that human values are belief that have importance to the holder, values instituted and important characteristics of self-concept and act as a supervisory principle for the persons. Human values are universal and are important consideration to take into account when interacting with the other pupils. So now here, just like a tree grows here, this is the plant grows and one by one leaves are coming in the same way. The person should have, a woman should have this value. So all the 12 values should have, and last is the industry. So one by one, see here the development of these values among the pupils. And great Mahatma Gandhi says that the story behind it that you must bring the change in yourself if you wish to see the change in the world. So it means that first of all we have to change ourselves, then we can bring the change in the world. So here this is the important thing. And if you want something new, that is innovative materials or innovative ideas, then accept the challenge and we have to think differently. And this is given by George Patton, says that make a change for the better. If everyone is thinking alike, then somebody is not thinking. So this is the quote given by George Patton. And also here, Albert Einstein says that if you always do what you always did, you will always get what you always got. So this is the thing given by this Albert Einstein. And also here, the important thing is that next is the Thomas Edison, great scientist, says that a great innovative only happens when people are not afraid to do things differently. This is given by George Cantor. And the Thomas Edison says that there is a way to do it better, find it. So these are the great scientists have given different information to us. And here from the scientific endeavor, we can say that learn from the yesterday, live for the today, hope for tomorrow, and the important thing is to that do not stop questioning. So this is the thing is given by Albert Einstein, says that those who have not committed any mistake have never tried to do something new. So this is given by Einstein and says that something is new. So what is now here? And here that Roosevelt has said that great mind discuss ideas, average mind discuss things, and small minds discuss people. And in addition to this, that this Swami Vivekananda says that take a risk in your life. If you win, you may lead. If you lose, you may guide. So this is the thing given by this Vivekananda. And after this now here, we can say that that in Hindi we can say that विज्ञान कहता है जीभ पर लगी चोट सबसे जल्दी ठीक होती है और ज्ञान कहता है जीभ से लगी चोट कभी ठीक नहीं होती. So this is the important part. As we know that when we say something, when we are working somewhere and someone says something to other in a arrogantly, so what is now? He also asking some that is he's saying sorry, and he's also another person is excuse him. But also what he says, he's a long time. He always remember after 1 year, after 4 years, 5 years. So so that is why this is the thing that we have to remember when we are talking with the others. And now when we come to the material here, that chemistry is the main subject related to the societal needs, and it is the central science. And so we can say that chemistry invent and synthesize the molecule, physicists characterize the molecule, biologists make use of molecules, and engineers fabricate the devices out of molecules, and public enjoy the molecule in different forms. So these are the things that we are in this material. And as we know that science and technology solve the problems in order to understand the natural world. Science and technology is there to know what the world is made of, what forces exist, and what law control the nature. Science and technology solve the problems in order to improve the lives of pupils. Science and technology try to find out what are the causes of disease and try to find out the cure. And a researcher who bring technology to the consumer is a scientist, engineers, and technologist. So, and here, as we know that the backbone of this sustainable development is the science and technology. And science and technology are different, but at the same time, they are complementary with each other. Science is the pursuit of knowledge. So someone can say, what is science? Science is the pursuit of knowledge and understanding for its own sake. And technology is the creation of artifacts for the system or the system to meet the people needs. And material are the backbone of the all technology, development of this technology. And it is rightly said that those who control the material control the technology. And as we know that material science and material scientists play an important role in the development of country. Now question is, what is material then? Material are solids which can be tailored to develop the desired properties applied for fabrication of devices leading to the societal benefits, and the properties are because of these being solids. As we know that properties of the materials are size dependent, and material scientists claim that 21st century is the century of material and especially the nanomaterials. So this is the, and this engineers can design this material as per the requirement, as per the pupil needs. And now if you go to the history and in the development of history, we can say that there are the first of all the Stone Age, then after that Bronze Age came, then Iron Age, and then Information Age, and after that Polymer Age, and after is also the what is the Silicon Age. Now it is a change, and now this is the time that is the Advanced Material Age, and it includes all the nanomaterials and nanoparticles. These are the new material. And nanofibers, so many materials are there, biomaterials are there, and in this case, and we can say that material. So what is material science and engineering? So we can say that advancement of science, structural property, correlation of material with the and to understood, and the new discipline of science which is known as material sciences came out. So the materials are there and development of material. So there is a branch of material which is known as the material science discipline. And whenever we are discussing with the material, there are 4 processes and 4 pillars are there. One is a processing, and after that the structure, after that properties and performance. So these are the 4 pillars. When we are synthesizing or we are having these are the 4 pillars to characterize the material. So whether it is formed or not. So processing. So processing means we should, what are the methods we applied or we are using for the synthesis purpose. Then structure, there should be some definite arrangement of the particles, atomic, macroscopic, and also we have to study the properties, that is their characterization, what are the that is mechanical, electrical, thermal, magnetic, and optical properties, and also then performance. So what is the behavior of that material for whatever we are making the material for what purpose. So there is application of this material, lot of applications are there, and these are the 4 pillars to characterize the synthesized materials. Whenever we are synthesizing also here, when we combine metal or ceramic, we get the composite. Any 2 materials, polymer ceramic, polymer metal, we can combine. So 1 + 1 we get A + B, we get the composite. So composite can be obtained by the combination of any 2 here is shown in this way. And more information we get here, that combination of these 2 things, that is here is the triangle is shown, and this triangle shows 3 parts. One is a science, here see, and this is the technology and innovation. So it gives different, science gives the advanced knowledge, and here technology gives the gainful and useful knowledge, whereas the innovation is the leadership in the usable knowledge. And now this another national prosperity shows that there are the 3 part again now, that is the scholarship driven first, second is the market driven, third is the competition driven. So this is the triangle which shows the national prosperity among in the country or among us here. So this is very important, and these are the 3 parts. When now materials continue to change the world, so whatever the technology depends on the materials, and here different types of materials are there, that is advancement in the materials, technology and science create and there is a continued advancement and in different sections. So here three are the advancement, that is technology advancement, science advancement, material advancement. So we can combine any two technology, and we get new technology, that is something new. And in the next part now, so whenever we are discussing about this new material, what is called nano size. So what is the nano size? We can say that nano is the word. Nano is taken from the Greek word which is known as nano, meaning is dwarf. It is a prefix used to describe 1 billionth of something. And we can say that, and this is the expression, that is 10 to the power minus 9 is the nano. And this is the scale, shows the conversion from meter to millimeter, and then millimeter to the micron, micron to nanometer. So 10 to the power minus 9 is the nanometer. And what is now diameter of one hydrogen atom is 0.1 nanometer. And now here, particle less than 100 nanometer in diameter are said to be a nanomaterials. And the study of such type of material, we say that it is a nanoscience. And nanotechnology is the branch which includes the design, characterization, production, and application of the synthesized material, and in the form of device, and it can be controlled in the form of shape, size, in nanoscale. This is the branch which is known as the nanotechnology. So this is about the nano size and nanomaterials. So whenever we are discussing nanomaterial, these are the four important application and four areas where it is useful: industry, food, agriculture, biomedical, environmental. So in all the parts, it is very, very useful. In case of environmental, we control the pollution, we minimize the, there are so many materials, so many devices, so many nano paints are there, which control the environmental pollution. So in this case also food packaging, so many materials are there we are using. And also in medical field, everywhere we find here now, this new technology have been using for the drug delivery and other parts, other things. So here, and for reinforcing plastic. So there is a very revolutionary change is taking place in different field because of this material. And now one of the important part of this is the nano gold. As we know, what is nano gold, and we have seen the bulk gold. And in case of nano gold, particle can also be synthesized. And for this, if you want to synthesize, this is the reaction is shown. For this case, we have to reduce the chloruric acid. This is the formula of chloruric acid. And this, after dissolving this acid in a rapidly stirred and reducing agent sodium citrate, we have to add. And we get this metallic silver. So this is the this is the chloruric acid. This is the sodium citrate added. When we get this is the carbon dioxide is get evolved and some carboxylic acid. And here we get the metallic nano gold. So nano gold, this nano gold may be one dimensional, two dimensional, three dimensional. When it is one dimensional, show this shape structure is like a nano rod, nano wire, nano tube, nano belt, like that. If it is a two dimensional, nano gold particles may have the morphology like or the structure like nanoplates, such as star, pentagon, squares, rectangles, and nanoplates, hexagon, like that. We obtain the material like this. And in case of it is a three dimensional, then it show the gold nano tadpoles, like a gold nano dumbbell shapes type. What is now nanopores or nanostar, and dendrites type or comb like structure may also we get in this case. And now, as we know, as the size change, the properties also changes. So changing in the size, that is when it is a material in the nano size, show the change in the properties. Some properties have been shown here about this nano gold. When nano gold in a bulk or in a colloidal form, it is golden in it is a golden in color. So as we have seen, golden color it is used for this making the ornaments. And now here the temperature melting point of this nano bulk gold or colloidal gold is 1064, and color is a golden. But as the size decreases, size in a nanometer size. So if it is a 1 nanometer gold particle, the temperature here see the color brown yellow. When it is a 20 nanometers in color in size, then red color gold nanoparticles. When it is a 100 nanometer in size, purple pink color. So see the different colors of this material depending upon the size. So this color changes with the change of particle size. And also when the this compound, that is a gold, is in a bulk, then it is having a face center cubic FCC structure. But when it is in a nano size, then it is having a icosahedral structure. And also shown here, we see the here as the size decreases, the color also intensity is also here increases. So these properties, if the materials are in a smaller size or in a nano size, show the change in the properties. So particles are so small that electrons are not free to move about as in the bulk gold, but in the moment become restricted. As a result, the particle interact differently with the light. Therefore, these are the causes of this material on the properties. And now this is the slide which shows the gold nanoparticles can be used for the nanomedicine. Here shown some areas, and here some this is the for the diagnostic, for drug delivery. We can here by with the help of this we can inject this drug which are in a nano size, and it repair the infected part. Also get after repairing it get digested because it is DNA based. So this type of anti microbial activities, and also for the therapeutic uses it can be used for this and treatment of diseases. This therapeutic means the it can be used for the treatment of diseases and action of remedial agents. So these are the some the application of these nano gold nanoparticles. And similar to these nano gold particles, silver nano particles are also there, and this can also be synthesized in a green root method, that is by using a plant extract, or the here this is the neem extract is shown, and also from the neem extract we can we can also synthesize by reducing this extract by using a sodium borohydride generally used, and some other reducing agents are also there, but now this is generally used, and we get silver from this neem extract, silver nanoparticle. The reaction is shown here, how we get this material, and after that also this after getting this silver nanoparticle, see the intensity of the color. So it is get darker and darker intensity of the color from light color to the transparent to the dark brownish color. So it is show as the size changes, particle size changes, then it is show the change in the color and some properties. So this is one of the way that we can synthesize the silver nanoparticle from the plant extract. And also these are the applications of this silver nanoparticle. Number of applications are there in every field of this. See here for the water treatment, for drug carrier, cosmetics, and antiviral. So see, these are the number of applications are there of the silver nanoparticle, and there are number of methods also there. Modern methods are there for the synthesis of silver nanoparticle. And now in case of application of the silver nanoparticle, as we know that these silver ions are nowadays using in the washing machine and also refrigerator, also in the air conditioning to sterilize and remove the bacteria and odors. And now nowadays in washing machine also it is written on the front that it is a nano silver coated, and here this is because of nano silver it remove the odor and also the removing the bacteria. And these are the some examples shown here, that a nanomaterial embedded in the cotton bandage, and this is in a hand gloves, and also in an apron also embedded in the apron. This is the nano fabric made by the silver materials, nanoparticles. And this slide shows the zinc oxide, nano zinc oxide. Zinc oxide can be synthesized in the laboratory by Sol-Gel method, and number of modern methods are there, hydrothermal or the solvothermal methods, and we get the different morphology with the different solvent also. And here zinc oxide can be synthesized by the Sol-Gel method, and also some other methods. Number of methods are there, and these are the different morphology shown in this slide, that these materials after synthesis show the morphology of different type. Some are the nano belt, some are nano helix type, nano wire type, nano comb type. See here nano helix, like that different nature we nano ring. So here in this way nanotubes, different types of morphology we obtain for this material. And in case of zinc oxide, it is very important material and have number of applications. And in this case, as we know, when the zinc oxide, this metal oxide is in a larger in size, then it block the UV light, scatter visible light, appear white. See here, this is a picture. And if you take the paste of this, and if you use for this in a sunscreen, for example, and paste it on the face, then it look like a white in this way. And as we know, in the old days, in the cricket matches also, players are using this sunscreen, and therefore their faces look like a white. We have seen in old time, but now this large size particle now been replaced by nano size zinc oxide particles, and it also block the UV light, so small compared to the wavelength of visible light that they do not scatter it and appear clear when these materials are using smaller size particles in the that is the sunscreen, if you place on the face also, it is now appear clear, not it is in a white. So these are the important characteristics of this nano size material. This zinc oxide can also be used as a supplement to the catfish, and it is shown one observation that here, if this here the addition of zinc oxide shown here, and here is the weight gain. So after this up to 1/6, so it is observed that there is an increase in the weight of the addition after some time. So if you give the feed to the fish, then the weight of this is also increases, and after some there is a gain is observed after 7 weeks. Here one this presence of zinc oxide after the 7 weeks, we observe that there is a gain in the weight of this fish. And now whenever we are also discussing the material that is nanomaterials, there are two types of carbon nanotubes, and number of methods are there to synthesize the carbon nanotubes. And here the carbon nanotube may be a single wall or the multi-walled carbon nanotubes are there. And when we are discussing the nanotechnology, we should also know what is carbon nanotubes. So in this case, one important method is given already. Pankaj Koinkar sir have discussed the synthesis of that is the nanotube by laser ablation methods. And here this is the another method which is known as the what is the CVD method. And in this case, CVD method, carbon nanotube can be synthesized, and arrangement for this is shown here. That this method shows the ferrocene we have to take in this reservoir, and after that here we have argon carrier gas we have to pass from this, and here is the ferrocene in benzene in a solution, and here is a K type of thermocouples, and after that we have to pass the solution through this because of this K type thermocouple, and here is some gases exhaust is here. So after making this arrangement, also this is simple method, and when the solution comes here, then it strikes, and what is we get by this method, the materials we obtain which are contains the large number of carbon nanotubes. So this is the one method, CVD, chemical vapor deposition method, for synthesis of these carbon nanotubes. And once we synthesize the carbon nanotube by laser ablation methods or by the CVD method, and this also having number of application of this carbon nanotube CNT, have this see some areas have been shown where it is mostly useful for this CNT material. And as we know that carbon nanotubes are being used to develop flat screen. Nowadays, TV screen has also been replaced because of the new technology, and new materials are coming day by day now here. And in the future also, it is said that TV screen should be a very thin, ultra light, and also foldable. So it is possible, and here this is the foldable screen shown here, PC, and so our TV screen may be very thin like a paper and can be folded and can be carried easily to and also lighter weight. So these are the it is because of this use of the carbon nanotubes. As we know, CNT also used in the that is this chip can be used in somewhere. That is instead of silicon, we can also use this new technology that is made by the carbon nanotube chip, and it is having large surface area, and because of that, this having larger surface, what is the largest large storage capacity. So it can also be used in place of this. What is the we say silicon in the ATM card, or in what is now we say laptops, or in smart mobiles. Also we use this chip in that devices. And another application of this what is we can say this CNT, that is a badminton racket, can also be made by this CNT. Because of this, it is very lightweight and also durable. It is tough and strong, and because of this nanocarbon tube, it is a tough material, and it can also be used in a board to make the bicycle, and which is nowadays the bicycles are also coming in the market with a very lightweight, and because of this they are using this type of material. And CNT also can be used in a textile, have a number of applications. See now here the nano fabrics are going to synthesize, and they are having number of different types of application. And so see some other applications: supercapacitor, create resistant fabric, conductivity textiles. Number of applications are there of the CNT in the textile also. So different applications are there. We can synthesize the material as per the requirement application of that material. one application of this CNT is also shown here is that it is an instant conform place to environment. So it is very environmentally friendly and can be useful, and it can also, this material can be manipulated in the light also to make the soldier invisible. It also have a, if you attach the sensor some, so it is having some physical condition and location, it also working properly, and also show some view radio communication directly into the uniform of the fabrics, and therefore it provide the chemical and biological protection. So it is useful to the soldiers in the military to wear such type of material, that is the, we can say it is a jacket made by these nano fabrics. So it is very beneficial to our military soldiers. Another one application, it is also we have observed that that is the, what is the effect of CNT on the hydration of this cement. As we know here, this graph is shown, plain cement is taken, and what is the here the strength of this material, compressive strength is shown here, and when the cement is mixed with the single wall, then what is the efficiency slightly increases, here strength slightly increases, but when we mix with the multi-wall carbon nanotube, then the 30% increase in the strength of this cement is there. And also there are three types of material, that is the plain cement have this type of morphology, and the cement with the single walled is shown here, this type of nature. So, and here is, you know, why this material increases the strength shown here, that is the cement mixed with the multi-wall. So the nature is shown here. So it, as compared to this, it is very compact, and what is, because of they give the more strength, and also that is, it is durable. So what is now here, so hydration can take place in this process by mixing this multi-wall carbon nanotubes. So it becomes stronger, and what is now tough. And now another application here, that is, it is these materials can also be useful. Different ingredients can be used. Here is shown the some parts of the stem, here root, stem, leaf of this plant, and see 1, 2, 3, 4, and there also we can give some carbon nanotubes, some nutrient to this. Then what is, they germinate, and they show the growth and development, and they, without any toxic effect. So here is also shown some what is the effect of carbon nanotubes shown here. So we can give, these are the materials have been shown step by step. If you give this CNT, so what is potassium, calcium, iron, water uptake during this, and what is now they show the some, so we have to give this micronutrient and to this plant, so they develop and give the more yield. So in this way, so step by step they have given here all the what things we can provide step by step. So here at this stage, second stage, third stage, fourth stage. So they are useful for this also to grow and develop. Now here one important that we should also know about this water purification. Carbon nanotube are useful for the purification of the water, and also to control the pollution. And here water pollution are to remove the toxic material from the wastewater. So here rhodamine B and methyl orange, two graphs have been shown. So as the time wavelength increases, so see here there is a absorbance is shown. So there is a this peak is increases step by step here as this here in case of this first rhodamine B, and so it is possible to we can control this purification by using this carbon nanotube. So addition of this this material can be used to control the pollution, also to control the to remove some that is the some toxic metals are there, or some like this color metals are there. It is possible to remove by using these carbon nanotubes. And here this is the thing that we use this for the nano titanium dioxide can be used as a photo catalyst, and generally it is good, very good material that we can use TiO2 for the for photocatalyst. And in this case here is shown this is the valence band and this is the conduction band, and here the reaction is taking place, that is called oxidational reduction. And here this here is the oxidation loss of here electrons. This is the reaction which is taking place here, and reduction reaction, gain of electron is shown here. And here TiO2 absorbs some amount energy and from the sun, and they give this So in this case, they after absorbing, see valence band and the conduction band. So this is the band gap. And as we know, nano TiO2 are the form of colloids. And because of this surface is possibly charged and positively charged, the surface is there. And mutual repulsion can stabilize the dispersion in the water without causing sedimentation. Isoelectric point of this material is a 6.25 and a band gap energy of the this is decreased as its optical response shifted to longer excitation wavelength, and minimum band gap is there. And because of this, it can be used, and also it is used for the reduction of pollution. And now in the next slide, we have shown here that these nanocomposites materials maybe are zero dimensional, one dimensional, two dimensional, are embedded in the metals, ceramic, and polymer matrix. So here, this is the non-polymer based materials: metal ceramic, and polymer based. They just shown some nanocomposites. So because after that CNT can be mixed to any material, can be metal ceramic, polymer metal, polymer ceramic can be, and we can have this type of different types of combination, non-polymer based and polymer based. These nanocomposites also have number of applications in the different field. And here, one application is shown that nanocomposites can be used as a sensor, structure, storage, solar cell. So these are the some areas where it is useful, and water purification, aerospace, in automobile, biomedical applications. And here is shown, this is the Mercedes, and having see the different part of this car, and nanomaterial in a fuel cell can be used. Nanofilm can also be used as a cell cleaning. So these are the some fuel additive. It can be nanocomposite coating is there. So these are the where we use this nanocomposite or nanomaterial for the different parts of this, making this smart car. And now important application of this is now here also. Another important part in this case is the another material that is called the superconductivity. As we know, what is superconductors have zero electrical resistance, and also we can say that superconductivity is the set of physical properties observed in certain material where the electrical resistance vanishes and magnetic flux field are expelled from the material. Any material existing these properties is a superconductor. And now here this is shown. What is this? Here this is the superconductor, here is the semiconductor, and this is the metal, this is the critical temperature. So superconductor, here temperature is shown, and this metal, and here is the superconductor. So then here is the so this is the area shown here. And by using this superconducting material, as we know, superconductor expel all the magnetic flux from their interior, and so force out magnetic field. So here is the Meissner effect. Show this type of effect. This is the field. Here T is greater than critical temperature, T is less than temperature. So depending upon this these lines, magnetic lines, see here passing through the material, and here not through the outside the material, that is through the vacuum. So two different fields are shown by this Meissner effect, and superconductor expel all these thing. And now based on this property, there is a here now see the next slide here. Superconductor can float and levitate above the magnetic field. So here is the magnetic field which is given, and this is the here this he see the movement of this material. And so this is the technology developed by the in the Japan also first time, and also because of that they develop such type of material, and Japanese made this type of experimental frictionless train and that float above the magnetic track, and with the speed of greater than 500 km/h. And here in the future the train can run in this way. See there here in this slide that how this is the magnetic route, this track, and it is not touching, it is frictionless, and this train is working on this superconducting material. And so see the speed is also much more as compared to our this nowadays train. So it is a very useful material. And next is also it is useful for the this superconductor in MRI, the conductor used in the modern superconducting, that is the for the scanning. And material used is a niobium titanium that becomes a superconductive at particular temperature. And here liquid helium we have to use. So it is also useful for the MRI, for taking the MRI of the body. And in addition to that, there are some smart materials also there. And the smart materials are the material that change its characteristics in terms of electrical, mechanical appearance, and also size and even shape when exposed to the particular conditions like light, magnetic field, electrical power, like that. So these are there are many different types of smart materials. They show the change, color changing material, light emitting, moving material, self assembling, so thickness changing. So different types of smart materials are there. And out of this, one material is here shown, that is the color changing material. Color of the as we know, some nowadays also we see some t-shirts, and which is made here on the t-shirt, on the back side or front side. This is the some design and also coated with that material, so that it is also known as a photochromic or thermochromic effect. If you photo means light and thermo means heat. So if you go in a that is sun rays, or if you go in the light, then you show the photochromic effect. This is UV photochromic t-shirt, and showed some emission of colors, and when exposed to the UV light. So in the dark they are not showing any color, but when we go to the outside, they show shining and also show colors. So these are the some color changing colors. Change of color of the materials are there due to light or heat, and therefore they are known as photochromic or thermochromic effect. And also as we know that there are some cups made by these some materials, and they show when it is a hot, then show appears caution hot. So when it is cold, it is not showing any message, but when it is hot, show this. So there is also some it appears message. So it is a blue to colorless, and it being used to hide message. And this copy cup, like a copy cup here, and message appear when it is a too hot or too cold. So they show some changing in the here. This is the cup made by the cotton, or here also in a t-shirt. Another important property that is shown here, that here one compound. This is the colorless. This compound 2,5 dimethyl methylisophenolaldehyde. This is the dimethyl lisophenolaldehyde. It is a colorless, but now it is exposed to it in a dark. But when it absorbs some light, what it is changes the color and photochromics. And so here, when it is hot, when we this is the leucodye, because of it is so here the how it is working shown here. Liquid crystal closure together. So when the rays comes and blue reflected the light, when it is cold, they show the red reflected light. So depending upon the materials, they show reflected blue color or red color or different color, and depending upon the whether the it is hot or cold. So this cup show the this type of changes. So this is the leucodye. Can be used when it is cold, colorless. When it is in a dark, it is colorless. When it absorbs some light, show the some photochromism. So, and also we know this phenomena that photochromic lenses. Already we know that photochromic lenses are the lenses that in a dark they show transparent, but when we expose this to the UV radiation, they show a darker color. And here they and also when again we come to the dark, they come gradually their original in a state. So photochromic lenses may be made either by glass, that is normally by microcrystalline silver halides, usually silver chloride, and also made by the plastic fibers are there, which are the organic in nature. So these photochromic lenses are also there, and there are also some materials which can be used for this purpose. And here some environmental friendly polymers are there, and we can also make some biodegradable polymers. What is nowadays there is a problem of this decomposition of this plastic material, and some are there that is also called PHB, that is poly beta hydroxybutylene PHB material can be synthesized by which is a biodegradable. It is not totally, but what is slow biodegradation is there, and this material is having number of applications. And so this is biodegradable polymer. And this is the it can also be used and what is now LED, and in case of conventional LED are made by using different different materials here: aluminum, gallium arsenic, red and infrared. So these are the material: gallium, phosphorus, green. So different colors they emit in case of LED. And Thomas Edison is the first to introduce this incandescent bulb in 1880, and this is converted electricity into the artificial light. So there are different types of LED materials nowadays, and work is going on this part, and they show different types of LED light and materials. And here is shown by use of that different types of here is shown candle, how much it gives, bulb, and this is CFL, and LED now came. So step by step, what there is a we can say the development is there, and now this how LED OLED means organic LED is also there, synthesized by using the organic materials. And this is the here this they give the light, and arrangement is there like sandwich here. This is the first layer, this is second layer, this is metallic cathode, and this is the anode, transparent and conductive anode. This is the material, organic material shown here. So this is anode and cathode, and in the middle there is an organic material which show the color here, so emit the light. And there are number of advantages of this OLED as compared to the LED materials, because it is brighter, clearer and thinner, lighter, and also they very lightweight, can be printed on the various surfaces also. So this OLED have number of applications. And another application of the different types of material, that it is also this lithium is very useful material, and lithium powered heart, this is shown here. This is the miracle of the science and cardiac pacemaker, and operate on the battery. So this is the one of the important part of the material, that is lithium powered heart can be here now in medical field. And this is developed by this professor chemistry Robert West, and power this tiny micro stimulator, a device that effectively jump start broken nerve connections in condition like Parkinson, epilepsy, and incontinence. So different types of here in case of diseases, this is a useful material. Now there are different types of energy sources, non-renewable, renewable sources. In case of non-renewable, oil, natural gas, coal, nuclear energy, renewable sun energy. So these energy sources have number of applications, and here we use here shown one solar cell, useful for the solar cell, photovoltaic cell. And so here in this case, this is the sun rays coming from this, and this is the transparent conducting oxide, zinc oxide. And here electrolyte is we have to take in the this is the one of the cell, and here is a platinum counter electrode. And this is a anode, reaction is taking place. Cathode, at anode there is a loss of electron. Cathode, there is a, so see there is the acceptance of electrons. So these two reactions, anode and cathode, are in this case taking place, and quantum dot synthesized solar cell can be increase the efficiency about 8%. So by using this here that solar cell, that is TiO2 generally used also here, and zinc oxide can also be used, and in this voltaic cell, and they give a lot of energy, solar cell energy, or different types of energy here we get. And here another slide shows the what is the Portland cement. As we know, cement, simple cement, and Portland cement is simple, and this is the composition of this cement is shown. It contains silica, iron oxide, and also some part of calcium carbonate. When it is passing through the kiln at this temperature, show some changes are there. So this is the process, and they show here is also percentage shown. And after passing through this kiln, what is gypsum? We generally is present in the cement, and the clinker is added. After passing through this kiln, we get the finished cement, and this cement very useful in this this final cement have huge amount of energy and huge amount of good quality limestone. And these two emit large amount of CO2 gas, but in this case there is very less emission of the carbon. As we know, the 1 ton of the Portland simple cement produces 1 ton of the carbon dioxide, which increases the global that is global warming. That is because of this greenhouse effect. And because of this emission, if there is a large emission of CO2, then we say that it is greenhouse gases are more, and because of this global warming may take place. So so we have to pass this cement instead of passing through this using simple CO2, pass through this, so the properties get changed and we get the finished cement. And this is very useful, and it also give the less emission of the CO2 gas, and so we can reduce the pollution also in this way. And some environmental issues associated with the carbon dioxide emission is there, and there is some sources that consumption and high energy play a leading role in the sustainable development of the cement and concrete industry. And therefore we have to use the reduced clinker content, applying this new technology to the material in case of this in this field of cement industry. and so we can reduce the carbon dioxide emission in a smaller quantities. So there may be a we can reduce the carbon dioxide gas in the air. And here another slide, it shows that what is that geopolymerization technology is also there, and this is the technology geopolymerization, and this is the new technology transform aluminum silicate material into the useful product, which is also called the geopolymers. And this is the some process have been shown. This is the aluminum silicate sources material. After curing, we get geopolymers, and these geopolymers, gel or concrete, also very useful material. And there are here this slide shows the sources of emission of this CO2. So here transportation fuel 19.2%, industrial process so 20.6%, and here power stations so different. So day by day there is an increase of this waste materials, that is and gases CO2 day by day increasing, because see this is the shown how the emission of the CO2 take place from different field. And so now here carbon dioxide can be changes into ethanol by breakdown through the study. So now scientists are also try to working on this part, that how to convert CO2 into the different useful material, and to minimize this greenhouse effect, decrease these gases, and also it can be useful to the society. So here they are trying, and different research in different area here is going on. And one of the method is shown here, that CO2 can be react with this. This is the one procedure, that is copper nanoparticles as a sphere. Here is been used embedded in the carbon nano spikes and convert the carbon dioxide into ethanol. So it is this is the process that CO2 can be converted into ethyl alcohol, and most of the greenhouse gas can be minimized by using this method. And so this is the one of the way that we can minimize this gas CO2. And this is the procedure shown here, that conversion of CO2 into carbon nanotube. Also scientists are working on this, and how to convert this into the carbon nanotube. So some process is shown here, that is this is the anode material. Here this is the anode nickel, here is a cathode and steel. And what is now how they CO2, by taking the CO2 and by using carbon nanotube here at last we get the carbon nanotube. So this is the reaction. It is converted into CO3, then oxygen with the presence of oxygen in the air, and then we get the carbon nanotube as the here. So this is one procedure that we can, and some reactions have been shown here how it works. This is a lithium carbonate can be converted to carbon, and that is carbon nanotube, and different methods we have to use for this purpose. So net reaction is shown here, that is CO2 gas is converted into carbon nanotubes and oxygen gas is evolved. So this is another way to convert the CO2 into ethanol or convert into carbon nanotubes. And there are a number of application of this material that environmentally, and this is the one building is shown here. This is, I think this is we know that world tallest building, Burj Khalifa in the Dubai, and this here they have huge LED nano paint, and in nano paint TiO2 is present. It break down the organic and inorganic matters, and therefore it clean the environment and also reduce the pollution. Also it break down the organic matter, that is like formaldehyde present in the air, and also they get wash out with the rainwater. So this nano paint, we can say that self-cleaning cement is also they have used. So self-cleaning cement and also nano paint, both are useful for the environmental purpose, and for to save these tall buildings or the monuments and like that. So here cement innovations stop this acid rain also. So this cement coated that passing modified cement passing through the kiln, and that final cement can also be used, and it reduce the pollution. And in the now at the end of this summary, we have seen that is the different types of materials are there, and these materials are of different kind and have the number of applications for the society, and also we can use, and how what are the we have seen that what are the different methods are also there, and what are the characterization methods, and how what are the applications of different material in the for useful for the society, that we have seen some part. And we say that these are the multifunctional material. So in future, some of the some more multifunctional material may develop and also useful for this society. So these are the applications of this material, and which are very, very useful for our society, for the mankind also, we can say that, for the mankind. So here, these are the what is the multifunctional materials, what are the different types of material, and their journey from from beginning to the up to this. Nowadays, nanomaterials are having a lot of importance for in a different field. Thank you.
Thank you. Thank you, Dr. Gurnule sir. Very nice and informative presentation. Sir, there is a question.
Okay.
I will ask Mr. Sandeep Deve. Please unmute your. Please unmute yourself and ask the question. Mr. Sandeep Deve. Unmute. Hello. We are not connecting with him. Sir, there is some problem regarding the joining.
Okay.
With Mr. Sandeep Deve. If any questions from chat box. Carry on.
So my question is this: when the air condition
Hello.
Hello, sir. Can I audible to you?
Hello.
Hello, sir. Can I audible to you?
Yeah.
Question is there. When the air condition filter is washed during maintenance, does the nanomaterials gets washed away or not?
No, there is no washing of that material because it is embedded, and during working, some gases may emit. Okay, because it is a small quantity.
Okay. Sir, continue, please.
Okay.
When the air condition filter is washed during the maintenance, does the nanomaterial gets washed away or not?
No. Am I audible, na? So nanomaterial
Yes,
cannot be get washed. No, nanomaterial cannot get washed.
Okay, thank you, sir. So how to prepare nano titanium oxide?
So for synthesis of nano titanium dioxide, metal oxide can be synthesized by Sol-Gel method, hydrothermal method. Number of modern methods are there for synthesis. Okay, and Sol-Gel method also, by using this we can also synthesize. Some other methods are also there. Number of methods are there also given in a you can search, and number of methods are there for synthesis. For synthesis there is no problem. Okay, for the any metal oxides.
Okay, sir. Thank you. Thank you so much, sir. Thank you very much for sharing deep knowledge about nanomaterials and its application. Your session was full of zeal and valuable, sir. It will be a great pleasure for us to listen you again in our future events. Thank you so much for joining us. Thank you. Now we move towards the third speaker of today's e-conference. The eminent person is Dr. David O. Ubada from Department of Mechanical Engineering, Amado Bello University, Zaria, Nigeria. I will give a brief introduction. Dr. David Obara got the postdoctoral fellowship of Switzerland. He has also got patent in developing mechanical robust hydroxyapatite scaffolds for tissue. Dr. Obara is member of Nigerian Young Academy. It's my honor to invite young researcher Dr. David Obara. Please.
Okay, thank you very much. Am I audible?
Hello.
Can you hear me? Yeah,
Yes,
hello.
sir. You are audible, sir. You can continue.
Perfect.
Yes, sir. You are audible.
Okay. Let me start by thanking the organizers of this e-conference for inviting me to this wonderful occasion. It's my pleasure and a great honor to be amongst you all. Just as the follow-up to the other two presenters, have been discussing about advanced functional materials. And the two presenters before me have said a lot about experimental routes to the synthesis of advanced materials. Now, it is also very important to note that in as much as the experimental routes are of huge interest, it's also important that we consider also some computational techniques to be able to, obtain accurate data as to how these materials perform. You will agree with me that most of the multifunctional materials, when they are synthesized experimentally, of course, there are some trial and error methodologies. But of course, the computational methods over time has proven to be much more accurate in terms of providing data. So I'll be discussing a computational methodology based on density functional theory. And I will link it to the concepts of the electronic and band structure calculations of electron and hole transport layers in perovskite solar cells. Now, what is density functional theory? I'm sure that some of us here on this platform that are involved in computational techniques will be conversant with this methodology. It's a computational quantum mechanical modeling tool used in material science, physics, and chemistry, to obtain the electronic structure of many body systems. And when I say many body systems, I'm referring to atoms, to molecules, and of course, condensed phases. Now, density functional theory was proposed by Walter Kohn in 1965. Of course, some other methods have been there beforehand, which have now been used to provide solutions to the very popular Schrödinger equation of density functional theory. You have augmented plane wave method, and of course, the linearized augmented plane wave methods. These methods have been used to provide solutions to or complement the density functional theory. Now, the applications of this computational tool are used to obtain electronic structure for solids, for insulators, for covalently bonded systems. Of course, when you refer to surfaces and interfaces, most especially in catalysis, density functional theory can be of huge interest. And also when you consider electronic, optical, and magnetic properties of a host of materials, this computational technique can be of huge interest. Now, this brings me to the overview of this presentation. I'll be speaking briefly on atomic structure, also on the quantum mechanical treatment, why you need to use the density functional theory, and how these quantum mechanical systems can be solved. And I'm going to apply a bit of all of these to my current research interest, which is on perovskite solar cells. Typically, the challenge or challenges, if you like, for theorists nowadays has been, how to simulate large-scale applications, making them easy to analyze the data. Also, theorists have been very much involved in, providing a proper quantum mechanical treatment that is accurate, that can give, accurate data in terms of comparing with experimental routes. Also, theorists have been very interested in how efficient these computational tools are, and of course, how you can use these computational tools to calculate new properties. Now, to be able to bring about a proper mechanical treatment, just as I've said earlier, theorists are looking into how you could develop the density functional theory in terms of bringing about all of the functionals and approximations that makes it, much more accurate. And some of these functionals and approximations are, under the dynamic mean functional theory and also the green functional. These functionals help to make the density functional theory assumptions much more accurate. Also, in terms of efficiency, computational tools, you agree with me, makes these calculations much more faster. And also, we can tinker with some of the properties of the theoretical postulation to make direct comparison with experiment, which of course is very important moving forward. Now, under the atomic structure, just as I said earlier, the density functional theory is quite important in this regard, because under the atomic structure, in as much as you intend to use this functional theory to simulate very large applications, you could, of course, simulate a huge crystal in terms of a unit cell. Now, the unit cell, the crystal could be quite large. You could represent that large crystal by a unit cell, and that is what is referred to under the periodic boundary condition, where you refer to a big crystal as a unit cell, such that you could focus on that unit cell as a representative of the huge crystal, as it were. Now, the unit cell is repeated to infinity. Of course, if you have assumed that that crystal is represented by a unit cell, you also assume that this unit cell is represented to infinity, because this makes the calculations faster. Of course, typically a real crystal is finite if you are looking at it in real time, because of course, if you have a real crystal during experimental procedures, you will see that it has a whole lot of impurities, defects, and all of this. Now, this has everything to do with comparing your experimental methods to the computational methods. Of course, you should also understand that when you are applying this functional theory, of course, as we have even listened to earlier, the nanomaterials different from, of course, the bulk materials in itself. And of course, when applying this theory or this computational tool, symmetry helps. Because if you assume that your crystals are aligned, they are properly situated, it helps your calculations to be faster and in fact much more accurate. Now, in theory, normally, the atomic structures and input are very well defined. Of course, if you are inputting all of this data to your computational tool, you will want to assume that, or you want to make it in such a way that all the information that you put into that software are accurate. And of course, based on this, even artificial structures, fictitious structures can also be studied in theory. In experiments, in comparison to using theoretical approaches. In experiments, it is known that atomic structure is not perfectly known. Of course, if you have a material that you intend to work on, you may not be able to determine its atomic structure during experiments. Now, single crystals, powder crystals, microcrystals, samples, and nano are all characteristics of experimental procedures. And of course, during experiment, because for instance, if you are trying to understand the structure of a material using X-ray diffraction, you want to assume that there are a whole lot of disorder and defects. So in terms of comparing theoretical approaches and experimental approaches, it is agreed that theoretical approaches provide better or more accurate results. Now, what are the few solid state concepts, few condensed matter concepts that you must put into consideration when applying the density functional theory as a theoretical approach? One is the crystal structure. Of course, all unit cells lead to 7 crystal systems. You have the triclinic, you could have the monoclinic, hexagonal, tetragonal. This must be put into consideration as to the kind of material that you are investigating at a given point in time. Also, the Bravais lattice has everything to do with the unit lattice, because the Bravais lattice is just, a Fourier transform of, for instance, unit lattice. So of course, you must also understand the 14 representations of, these crystal systems, which, are all very similar to what you have during or under the unit lattice. Now, you must also put into considerations the symmetries of the physical system. Just as I've said earlier, what are the geometries? What are the geometries and how aligned are they? This must be put into consideration. This space group and the reciprocal lattice, which has everything to do with the beryllium zone, should also be put into consideration. Now, that is for the crystal structure when considering this theoretical approach. Under the electronic structure, you should look at the periodic boundary conditions. I mentioned that earlier, that if you are trying to consider a crystal and you want to examine it theoretically, you should consider that crystal as a unit cell. That enables you to be able to take that unit cell as a representative of the total system in itself. Also, the Bloch theorem and the Schrödinger equation, because the Schrödinger equation forms the basis for the calculation using DFT. Now, this Schrödinger equation, you must pick the appropriate method to be able to solve the Schrödinger equation. Typically, the Hartree-Fock method has been used, but nowadays, moving forward and trying to be more accurate, the density functional theory is of interest. Of course, under this quantum mechanical treatment, since the DFT is basically to calculate the electronic structure, or if you like, the ground state properties of many body systems, the main scheme is the density functional theory. This theory, it's a mean field approach that requires approximation. Just as I said, when I say it requires approximations, it enables the properties that you are calculating to the property that you are calculating to be much more accurate. All right. Now, of course, according to Kohn, it is sufficient to know that the electron density of a system determines its total energy. So if you know the electron density of any system, you could determine its total energy using this theory. So the many electron wave function helps you in this regard. Now, there are many schemes which, of course, complements the density functional theory. Just as I said earlier, of course, the density functional theory is accurate, but to make it much more accurate, some approximations are added to complement the theoretical approach. One of these is the Green function, which is basically for excitations or band gap calculation. Of course, when you have a body in ground state, as soon as that body is excited, it leaves the ground state and becomes in the excited state. So if you are now using density functional theory to observe or examine the excited state of a many body system, the Green function would be used as a complement to the density functional theory. Of course, the BSC equation can also be used as a complement to the density functional theory to be able to calculate the exciton, core, hole, electron, body interactions. And also, the dynamic mean field theory is also very important as it complements the DFT appropriately. Just as I mentioned earlier, the Schrödinger equation is a key equation when considering the density functional theory approach. And of course, there are a whole lot of concepts when solving this Schrödinger equations in solids. Now, if you can see some of those concepts I put there, I will just mention a few. I've mentioned earlier that, of course, for every particular many-body system, if you are approaching or applying the density functional theory, you would have to examine or take note of a whole lot of complements. Now, one is, the form of potential of that system. And one interesting form of potential is the pseudo potential. The pseudo potential has everything to do with the potential of all of the electrons very close to the nucleus of that system. Because we want to believe that when the body is excited, it takes a huge amount of energy for the electrons very close to the nucleus to be excited. So the pseudo potential helps to generalize all of these concepts, making the approximations much more accurate. Now, if you look at also the representation of the solid or the treatment of the spins, of course, for every electrons around a particular orbit, you should expect that it spins when excited. So when considering how to use the theoretical approach, you could also put all of these considerations into place. And also when you look at the exchange and correlation potential, as I said earlier, for you to be able to understand this concept, density functional theory is of huge interest, as to all other correlation theories like the Hartree-Fock, etc. So all of these concepts have to be put in place to be able to exactly determine the properties of a given many-body system. Now, how does the density functional theory compare to the many-body theory? Now, there are two communities in this regard. Now, under the local density approximation, under calculation of band structure, and comparing that to the many-body theory, you will see that under the local density approximation, which is typically a density functional theoretical approach, it is material specific, and it takes care of the first principle calculations, if you like, ab initio. And this approach, the DFT, is often successful, quantitatively. Of course, it gives quantitative data, and it's an effective one particular approach. When you compare this to the many-body theory systems, you will see that they have, some qualitative understanding as compared to the quantitative approach of the LDA rather. And of course, it shows that the DFT is a much more robust approach in this regard. Now, the grand challenge of using this computational methodology is finding a functional which leads to the DFT heaven. That means the functional that takes you to a state where you want to believe that all the data that you're obtaining are quite accurate. And this brings to the Pedus-Jacobs ladder, which he proposed, some years ago. He proposed that this particular ladder takes you to the DFT heaven, where when you apply the DFT approach, you'll be able to obtain very accurate results. Now, of course, as I said earlier, Hartree-Fock methodology has been, used to solve the conventional Schrödinger equation. Of course, because we need more accuracy, we need to add more functionals and more assumptions, and that goes, to the local density approximation. Of course, Hartree-Fock goes to the local density approximation, which means that applying the local density approximation, you should obtain more accurate results. Now, that also goes, if you're going up the ladder to get to where you have very accurate results, you could also consider the generalized gradient approximation, which is a step further from the local density approximation. And of course, going further from the generalized gradient approximation, you will see that there's the meta generalized gradient approximation as well. Now, all of these steps takes you to a point where the data obtained using the density functional theory is much more accurate. Of course, the density functional theory typically tries to solve various two equations. The Hohenberg-Combe theorem is, much more exact, and of course the Konsham, which is also still exact. Now, this density functional theory does the function of solving these equations as it relates to whatever materials properties that is of interest. So in a many-body problem of several interacting atoms or electrons, the nucleus is mapped to a one electron reference system, such that you regard it as a fictitious system where you have electrons not actually interacting. Because if you have electrons, if you assume that the electrons are interacting, the excited stage, it could make the body much more complex. So bringing it down to a level where you could, generally understand, you bring it down to a level where you assume that, there's a one electron reference system that leads to the same density of that system, and it makes it much more easier to solve. And that is the reasons why the Konsham and the Hohenberg-Combe theorem are of very huge interest in this computational approach. Now, moving forward to making sure that the approaches used or utilized are quite accurate. You could continually add the assumptions, the local density approximation and the gradient, the generalized gradient approximations. Now, these approximations, as I've said earlier, makes sure that the density functional theoretical approach, in solving some of these many-body systems are, quite accurate, and they are still very, very active in the field of research today. Of course, for the treatment of this exchange and correlation theorems, when applying the density functional theory, these approximations, as I've said earlier, are of interest. Now, the approximations, as they move now in this on this slide down the ladder, makes sure that the data that's obtained is much more accurate. The local density approximation, the generalized graded approximation, etc. Now, these approximations are of interest, and you should, or when anytime that these approximations are to be applied, it should be noted that it depends on the problem that the scientist is trying to solve. So you will decide on the particular approximation method to utilize. All right. Having said all of this, it's important to look for a way, or present a way that these theories can be applied to general scientific problems. Now, one case study that I've brought to the fore is the issue of synthesizing or fabricating perovskite solar cells. Now, of course, a whole lot of scientists have just gone straight to the experimental route of fabricating solar cells, and a whole lot of scientists have also tried to look at the properties of these solar cells theoretically. Now, considering fabricating or understanding the properties of a solar cell theoretically, I've put here a case study of investigating the performance of cerium oxide as an electron and hole transport layer for solution process perovskite solar cells. Now, of course, for an efficient perovskite solar cells, there are a whole lot of things to be considered. I will limit my discussion here to the electron transport layer. Now, if you look at this slide here, the electron transport layer is PCBM. Now, of course, if the electron transport layer can easily transport the carriers, or can easily carry carriers to the anode, it makes the power conversion efficiency of the solar cell much more interesting. So one could use the density functional theory to understand, the levels, the gaps, the band gaps that the electron transport layer possess, to be able to move electrons from the bottom or the top of the valence band to the bottom of the conduction band, because this is quite interesting in terms of how the solar cell device would perform. So the density functional theory can help in understanding, the band gap, in between the bottom of the conduction band and the top of the valence band, to be able to predict how much efficiency a particular electron transport layer would possess at a given point in time. Now considering titanium oxide as an electron transport layer, and also trying to see how much, or trying to investigate the energy levels, as it were. Of course, the density functional theoretical approach can be used in terms of understanding all of the energy levels for all the materials stacked together to produce the solar cell. Of course, the solar cell is made of the light absorbing layer, which is typically the perovskite, the electron transport layer, the hole transport layer, the anode, the cathode. So, of course, the density functional theory can be used to understand the energy levels of all of these materials stacked together, such that the power conversion efficiency of the solar cell can be properly obtained. And as you can see from the second schematic, it shows all of the energy levels for all of the materials, that have been stacked together. So you'll see that for the titanium oxide electron transport layer, you will see that the energy level, at the top of the valence band is 7.3, while at the top or the bottom of the conduction band is 4.1, which gives a reasonable band gap for power conversion efficiency to be improved upon. Of course, if you look at titanium oxide as electron transport layer, you will see that the electrons can move from one level to the other based on, the states at which these electrons are. And of course, the states at which these electrons are determine how efficient the transport layer would perform. So if you see, if you have electrons at the valence states, they are high in energy and they can quickly move from the bottom, from the top of the valence band to the bottom of the conduction band. Of course, these electrons in these states are delocalized. Now, when you consider the electrons at the semi-core states, of course, they have medium energy as compared to the ones, at the valence states. And of course, they are not completely confined, as you see when you have electrons in the core states. Now, electrons in all of these states determine how much of electron mobility can take place when titanium oxide is used as an electron transport layer in perovskite solar cells. Now, this is a typical methodological approach when the DFT is to be utilized. Now, one of the first things to consider during calculations is to consider the density of states of any system. When you consider the density of states, you could obtain by using the green approximation, in which you could express all of the electron self-energy as a product of a one-body Green function. Now, you could also look at all of the calculations and perform them under the beryllium zone at the center point only. Now, when you apply spin-orbit coupling, that enables for the correct assessment of the electronic properties of that one-body system using a typical suit, which is most useful, the quantum expressum suit, which has the DFT package. Now, when you are using this also, you could apply, of course, the generalized gradient approximation to obtain the exchange and correlation energy of the electron structure using the DFT calculations. And of course, if you look at the room temperature phases of the perovskite, you will also know that it takes it from the ground state to the excitation stage. So all of the considerations have to be put into place to see that the energies converge faster. And of course, you should also consider the lattice parameters and atomic positions when using the DFT. Now, one of the interesting codes to use when using the density functional theory is the plane wave self-consistent field theory. and it has, of course, its pros and cons. When considering this code during the DFT calculations, one of the advantages is that it can perform total energy calculations, which is quite interesting as far as this is concerned. Of course, as I mentioned earlier, it uses both studio potentials and ultra soft studio potentials to calculate all of the potential energies. Now, one of the disadvantages is that not all the elements of the periodic table are captured. So perhaps you need to check or investigate elements or elements in a particular row of a periodic table. If you are using this particular code, you may not be able to capture some of the elements that interest you. And also, of course, one interesting advantage is that the memory properties and tools are, very much within reach. Now, comparing this aspect of simulation to experiment, one of the interesting things when you are comparing using a theoretical approach and an experimental approach in obtaining materials properties is the structure model. Of course, when using theoretical approaches, you could accurately obtain the atomic structure of a given many-body system as compared to experimental approaches. The convergence, of course, is very much within reach when using the theoretical approach. And also, of course, in quantum mechanical modeling of the many-body systems, of course, the theoretical approach can help you to do a whole lot of comparison between the ground states and excited states of a particular experimental procedure. Of course, this aspect must be considered when you are looking or trying to consider or compare theoretical data and experimental data. And at this point, I will thank you very much for listening.
Okay, thank you, sir. Sir, can I be audible to you?
Yes, you're audible to me. I can hear you.
Okay, sir. One question is there from YouTube, sir. How to know which metal is more electron rich in organometallic complex by density functional theory? I will repeat the question, sir.
Okay,
how
please.
to know which metal is more electron rich in organometallic complex by density functional theory?
I didn't get that question properly. I don't know. Is he on the chat? Is he on the chat?
Okay.
Okay, I can hear you.
Question do?
One more question is there.
Sir.
Yeah, yes.
Am I audible to you?
Yes, you're audible.
Am I audible, sir?
Yes, I can hear you.
My question is that can we use alkali metal, alkaline earth metal as an electron transport material instead of titanium?
Okay.
You are saying that in your presentations you are using the titanium metals. Can we use alkali metals or alkaline earth metals in that particular electron transport material?
Yes, you could investigate if those materials, of course, they can be used. I've also in the past considered cerium oxide as an electron transport layer. Of course, you could also consider some alkaline earth or alkaline metals as transport whole or transport electron transport material. But of course, nowadays it has been proven or shown that titanium oxide is very much effective, as it normally has a faster charge carrier than even the light absorbing layer. So it's something that you could investigate, which is very possible. Okay.
Thank you, sir. Thank you very much for a nice presentation.
How does density functional theory help Study of nanoparticles.
You said, can density functional theory be used to, please, can you come again?
Hello, sir, I'm audible.
Yes, I can. Yes, you're audible to me.
How does density functional theory help in the study of nanoparticles?
Yes. That is, of course, that is possible, but it's going to be a bit tricky. Of course, you know, if you look at the approach, it depends on the particular property that you are interested in, carrying out. That should, determine if the density functional theory can be used for that system. If you want to consider, the ground state properties, of course, the nanoparticles can be used to, form a particular crystal system. So, of course, the density functional theory can be used as well. But what should always determine your selection of the density functional theory is to understand, the problem at hand. Are you trying to study the ground state properties? Are you trying to study excitation state properties, etc.? So that depends. That will, what they call it, determine if you could use density functional theory. But of course, you could use it if that particular nanoparticles have been used to, design or produce a particular body that you want to study.
Okay, thank you, sir. Thank you for sharing very informative knowledge about crystal structure, density functional theory, and electron transport mechanism. Thank you for joining us, sir. Thank you.
Okay, thank you.
Now we will move towards the next speaker, last speaker about the conference. It's my immense pleasure to introduce Dr. B.P. Kafle, Associate Professor, Department of Chemical Science and Engineering, Kathmandu University, Nepal. The area of research is material science, nanoparticles, spectroscopic clusters. I will invite Dr. B.P. Kafle sir from Nepal. So you are visible, sir. Sir, you are not audible, sir. Please check your earphones or microphones.
Yeah, okay. So thank you for unmuting. Yeah. So namaste to everyone. So I'm Bim Kafle, and I thank you organizers for wonderful meeting, and I hear wonderful talks by Professor Gundule and Professor David. It was wonderful to have impression about all the renewable energies by Professor Gurnule, and also as I myself is involved in perovskite solar cell. It was wonderful to have. I'm an experimentalist actually, so it was wonderful to have a theoretical insight on this material. So with this few words, I would like to present my work. Sorry. One minute, please. Sorry.
Okay, no problem.
So, title of my talk is nanomaterial processing for solar cell technology for low temperature plasma experience from Kathmandu University, and the topic is a bit for application to the plasma. We also use plasma, so I will speak less, but I will speak here on the solar cell stuffs, perovskite solar cell stuff. In the beginning, I will give a brief overview of perovskite solar cell and key parameters like optical properties of the optical properties, and also some parameters that controls the stability as well. And then I will discuss a little bit on the problem of PSC and the approaches scientists are trying to tackle with that, and devising this kind of solar cell. Where do we stand in not the global, but I would speak only our efforts in Kathmandu University, in my university, and then I will speak several layers that Professor David mentioned about the ETL layer and tissue layer, and also the perovskite layer. And then I will mainly focus on our effort on graphene oxide as a whole transport layer. So then I will conclude my talk. So as you know that many of us have been using in our home is mostly the silicon solar cell, and silicon solar cell is also called first generation because it was the first material to be used to my knowledge, and it has been widely used because of the efficiency, the best efficiency achieved. I mean, the best material to produce the solar cell because of the band gap, appropriate band gap for trapping the visible light, mostly the visible light. So, and another generation is thin film based solar cell. In the first generation, we cannot go. There is a theoretical limit of elevating the efficiency, and the theoretical limit is about 33% because of the main reason is because of the high percentage of solar radiation is reflected from the surface of this panel. And the another, as I mentioned, is the thin film base. This also has very limited efficiency that we cannot cross. That I will not be speaking much more about this. And my attention here is on the nanomaterial based solar cell technology that briefly mentioned by Professor Gurnule, the organic dye sensitized solar cell or quantum dot solar cells, or advanced concept like the emerging solar cell technology like perovskite solar cell. Actually, this perovskite this kind of solar cell technology has been emerging very rapidly, and they are considered as a source of energy, energy harvesting technologies to fulfill the future need of the energy. And I will show you a few examples, like this is the perovskite solar cell produced by this posted in MIT News last year. So it's very nice. You can see the metal coat on top, and this black material is a coat of the several layers. It contains, for example, main composition is perovskite, as Professor David said, and it contains, this is the metal contact, this yellow one here, maybe the gold I could see here, and the other layer is nickel oxide or any kind of electron, the whole transport layer, and the another one would be PCBM organic layer, or it can be inorganic layer as a electron transport, like Professor David explained about the TiO2, which is the most prominent, mostly used because of the fast charge transport properties, also matching of the band gap with perovskite. So matching of the conduction band of this material with the perovskite. this is very important of matching the band conduction band, the electrochemical potential. So I'm afraid I have not been reviewed this literature since 6 months. I'm afraid the efficiency has been improving in a month, every month of this kind of solar cell. To my knowledge, the perovskite solar cell maximum efficiency so far is about 25%, that is reported in NREL report in 2009, and that is already is very close to the efficiency realized in the silicon-based solar cell in the laboratory, where in the first generation solar cell like silicon, the efficiency cannot be, the panels that we use in our home or in a large scale has efficiency varies from, let's say, what kind of crystal you are using. It depends from 10% to maximum 20%. That is that are the product have that much of efficiency in the market, and that arise in the market. So with this achievement, scientists are hoping that this material could be very promising material for solar energy harvesting. And actually, if you look at the price of the solar energy, you can see now the silicon-based solar cell roughly cost about $1 or 50 cents, a bit higher per watt. But this is going down continuously because of the improvement in the silicon-based solar cell. But still, it is very expensive than the electricity produced by hydro or the coal or other non-renewable nuclear or other non-renewable sources. So we scientists need to work very hard to improve the efficiency so that we could reduce the carbon dioxide produced, that Professor Gurnule stressed, the carbon dioxide produced during the coal burning or petroleum gas burning, or other hazardous nuclear power running in the power plant. So this technology, the perovskite solar cell, has been already demonstrated in a large scale. For example, Michael Grazel is a discoverer of perovskite solar cell technology, mostly considered he the discoverer, and he in his lab, his lab was lightened with perovskite solar panels. You can see easily. So unfortunately, I could not hear. I don't know why. Maybe I will remove this slide so that not in the presentation mode. Sorry, I did not put in the presentation mode. Sorry, I will put in the presentation mode and then. Yes. So he is the Professor Michael Grazel from Austria. This panel, this kind of perovskite solar cell, comprises mostly one is perovskite solar cell, a perovskite layer. It's a thin layer of perovskite, and on top of that there is a hole transport layer, where once the hole is electron hole is created in this interface, then hole goes in this direction, electron goes towards the TiO2, and this TiO2 swiftly moves the charge towards the tissue layer, and the tissue layer is as a bridge and comes to the electrical contact. Like here, perovskite sends the electron here in the TiO2, and TiO2 gives to the FTO, and then we can trap that electron to our load, while hole goes on the other direction. That can be spirometred, and scientists, as this material is very organic material, is this one is expensive, and another is unstable with when you expose in the intense solar radiation of, like, say 600 to 1000 watt in the afternoon. It decomposes easily, and another problem with this organic molecule is quick decomposition with humidity, with oxygen, reaction with the reaction. So to overcome, scientists are trying to use inorganic material of this. As you can see, a glimpse of perovskite solar cells and application one could see in the backpack, or in the rooftop, or in the on the window. You can put anywhere. So because it, and they imagine, some of them already produce flexible, so you can put anywhere of your desire. So these are the components of the perovskite solar cell. As I said, this is the perovskite, and this is a whole transport layer and the electron transport layer. And the another one is FTO. Mostly we produce FTO, but it's a fluorine doped tin oxide. Tin oxide. It when you the light is passed, irradiated from in this direction, from back side, from this side, and this is glass is of course transparent, and this also should be transparent, but it should also be conductive to the electron, which when here electrons come from here to here and from here to here, and then you pass these electrons to the load, as I said before. So this layer should also be conductive, and the light passes from here to perovskite. This layer absorbs and it goes to the conduction band, and again this electron goes again to the conduction band of the TiO2. That's how this kind of solar cell works. And let's discuss the critical parameters that that define its performance. One is let's compare the band gap of the with the silicon and the perovskite solar cell. If you see here, this graph shows spectral response. Means you can see, I mean, you can imagine it's an absorption of the solar radiation as a function of wavelength, and solar radiation comprises a very few portion, something like 9% of the solar radiation comprises UV, that hardly comes to the on the Earth's surface, and mostly is of visible light. For example, 400 to 700, 400. Mostly the major component is it peaks around 500, 480 nanometer, and if you see the optical response of this, and what about 41% is IR radiation. So in our spectrum, solar spectrum, 9% is UV, about 50% is visible light, and about 41% is IR radiation. So if we have a material that can absorb mostly the visible and part of the IR, that would elevate the efficiency of the solar cell. And here in case of silicon, its band gap is about 1.1 eV. It means that it absorbs not only the visible light, but also the IR part of the IR radiation. So its efficiency is very good. In the same token, if you look in the absorption curve of the perovskite, it absorbs visible very nicely, and also all the way to somewhere it decreases, absorption decreases after 500, but it absorbs relatively nicely up to about 780 nanometer. After that, it goes down. Where in case of silicon, this is something like you might say 1.1 EV is something. This is about 1100 nanometer. Where in case of perovskite, it is only up to 780. So slightly larger band gap of the perovskite. If you see here, this graph calculates the band gap of the perovskite, and it's about 1.5 eV. So slightly only it can absorb visible light. If you can extend this region to the albeit towards the push towards the IR region, then you can enhance the efficiency. One approach is that photons impinging on the surface of the perovskite, and then how much photon is converted to the electron is depicted in this, can be represented in this curve, for example, as a function of wavelength. You see here, in this curve, very much the current conversion efficiency very much reflects the absorption curve here. Let's say up to 780 nanometer. Here also there's very good correlation, and we can see that about 60% of the solar radiation can be converted into photon, converted into electricity by this kind of material. And again, this is a nice crystal of the perovskite in a molecular level. Here, this molecule perovskite comprises. I would have defined it before actually. So contains is perovskite. I'm discussing here is methyl ammonium that comprises methyl ammonium lead iodide. People have been now tailoring with this iodide with various proportion of bromide and also chloride, but I will be discussing here only with this one. So it contains the methyl sheets here, and this carbon you can see here situated here with 3 H. These 3 H are here, and this blue dots are iodine, and lead is this is shown here. So this is a crystal molecular structure of the perovskite, and this is the single crystal of the nice single crystal of this material. You can see very nice crystal, single crystal, and the arrangement of this perovskite in with other all the components of the solar cell. So here I must have to mention the problem of this kind of solar cell. Although scientists already realize 20%, even in the laboratory, it has been already tested about 20% or so efficiency of this kind of solar cell in the standard tests. But it has a problem, is that is because it contains organic part. When sunlight comes in this material, it decomposes with the intense solar radiation. One is major problem is that. Another one is degradation with the when it comes into the moisture. This is the major challenge when we have to adapt. Our strategy is, and also for this is mostly used p-type semiconductor is spirometred. This is organic molecule, and this also when you export to the solar radiation is lithium doped, and this ion separates, and in general it decomposes. So its properties are lost. P-type semiconducting property are lost. So both of the layers decompose with moisture and intense solar radiation. So our approach is, if you could put an overcoat with a very strong overcoat, we could like putting overcoat in winter by us to protect from the winter's cold. So similarly, we can also put an overcoat that does not decompose with sun and moisture, and then we will be saving this material. Also, that material should also work as a p-type semiconductor. So our approach is using reduced graphene oxide. Is one of the derivative of the graphene. It's a graphene. Graphene, but few percent of oxygen containing on the interface of the graphene sheets. So people have already shown that's possible to use. For example, using spirometer has a poor performance and less stable, while using reduced graphene oxide, you can see here the stability is larger, and while the degradation with for example with 2000 hour exposure in the sun and our moisture, its performance degrade very largely with the organic p-type semiconductor, while with RGO it's very small loss. So we also wanted to test if it is feasible even in the developing countries like us with a very limited resource. I will explain here each layers briefly. So we more or less completed the key parameters and the problem. So I will be discussing where we stand. As we say, in our effort, we already managed to do produce FTO and TiO2. I will explain very briefly, and I will mostly focus on perovskite and in this layer production of this kind of layer. And that we this is the method that I will not explain here. Here for for preparing this layer in the TCO layer, I will very briefly mention here. Yes, to produce this FTO, we built our own homemade solar spray pyrolysis setup, and where you can put solution here and then spray with this very simple setup. And once the solution is sprayed here, the liquid goes up, and you can prepare a very nice film with a resistance of about very close to the transparent conducting of that is available in market. And after preparing this, we characterize, and the crystallinity also shows very nice features with very correlated with the published features. We also treated with plasma and plasma treatment. So for example, if you compare with these are the samples without treatment with plasma. Here with same sample but with treatment of the plasma, you can see this 2-1-1 crystal is enlarged. So you can see if you treat with plasma, the crystallinity also found to be changed. Anyway, we with our this homemade setup, we could produce a nice films with a good optical properties. Here you can see here this FTO layers transmission, which is very important because, as I said here, this as we expose solar radiation in this direction, this layer should be conductive as well as transparent. For this reason, we tested our film's transparency. For example, hello. Any suggestion? Any comment? Okay, so let me continue. Yeah. Yes. Any comment? Any suggestion?
No, sir. Continue, please.
Oh, okay. Sorry. So, so you can look here in the transmission. Transmission as this FTO, fluorine doped tin oxide, absorbed UV light, but it transmits all the visible lights. You can see here very nicely up to 85% transmission or above 80% transmission as achieved. And you can see here in general, I will not have much time to explain here, but you can see this is the electrical resistance of the as a function of time of deposition of the film. You can see with plasma, with nitrogen treated sample or plasma, they show very close properties. While if you expose if you calcinate it in air, that has a relatively higher electrical conductivity. But in general, you can see if you increase the thickness, I mean a slightly larger, for example, deposition from 15 minute, which is about roughly 300 nanometer. Okay, so 300 to 400 nanometer our film's thickness. With this thickness, we could very nicely observe the desired heat resistance of our film. And we also compare the grain size. You can see grain size is a function of deposition time. Grain size slightly decreased. You can see here with deposition time, it means the grain size decreased with the thickness, increasing the thickness. And while average reflection increased with average reflection increased with the time of deposition. Means the reflection increased with the thickness of the film. Here I already discussed about this heat resistance. Okay. sorry, that's maybe I will skip this. We published this result in AIP Advances for your kind information. So now I will go to the next step for how we prepare TiO2 layer and also the perovskite layer briefly. Here you can see this is FTO glass. On top of that, we prepared by Dr. Blading the TiO2 layer. And on top of this TiO2 layer, we prepared lead iodide only. This is coating of the methyl ammonium, preparing of methyl ammonium iodide is two-step. Briefly, I will explain here. How it is done is, first you prepare two precursors. One is methyl ammonium iodide and another is lead iodide. First, you prepare methyl ammonium iodide and spin coat like here, and then put another lead iodide and sandwich again with a methyl ammonium iodide and rotate it again. So once you prepare this kind of sandwich, then if you heat it up, let's say up to 70 degrees centigrade, then this color, it looks transparent in the beginning, but it become brownish, dark brownish after you heat it up, after you calcinate it. By the same process we also followed here. This is only lead iodide. You can see clearly the yellow color. And then after putting the perovskite on top of that by spin coating, we see very nice color. But in the edge, it was our initial effort. The color looked perfect and the absorption also looked perfect. I will show you here the absorption. Here we tested the crystallinity, only lead iodide. You can see very small particles here. After putting the methyl ammonium iodide, this rocky structures like very large particle size shows clear difference between putting the lead iodide and the methyl ammonium iodide, or it confirms the one indication of the formation of the perovskite. I will see more, optical and Raman peaks from here. For example, this is the spectra of this perovskite material. And these are, perovskite. So we tried actually in TiO2, not the Z, so it should be corrected actually. And then this blue one is FTO, and this is TiO2, as I said before. The red one is TiO2. You see, there is no absorption of this kind of large band gap because this contains large band gap about above 3, so they cannot absorb visible light. While on the other hand, perovskite has a very nice absorption and goes down after, let's say, very close to 800, as I said before. This is very much correlated in agreement with the previous results we discussed in the optical response of the perovskite material. These are, Raman spectra, and these peaks very corroborate with other papers. So, and also, appearance of this kind of functional groups, NH stretching, here NH bending, and presence of this, CH bend, these peaks in the IR spectra also confirms there is, of course, indication of nitrogen containing or carbon containing compound. That is what we are dealing with here in the perovskite contains, as I said, with carbon, nitrogen, and hydrogen. And also the lead, but we cannot see here in the signature. So we also published again this recently. It's initial effort, but we are very happy to have publication. And then we now move to the third step of our endeavor of perovskite solar cells synthesis. We started from simple graphite. We purchased graphite from India and then processed with Hammer's method. First produced into powder and then converted into liquid, this kind of lipid, by processing with KMNO4 and in this kind of chemicals. And then we compared their optical properties, and they look very close with the with these people other publications. You can see here, although our look a little bit much darker than there. So I will explain why maybe our a little bit our sample is a little bit darker. Once you, we wanted to reduce this GO, graphene oxide, into reduced graphene oxide. It means it contains a lot of oxygen. We wanted to remove it to RGO so that it will work as a whole transport layer. So our aim is to form this layer, this green one layer, and we checked the absorption, UV visible absorption, and of this solution, it corroborated very closely. Geo shows about 300, 200, yes, 231 nanometer at maxima at 231 nanometer. Ours shifted a bit higher to the red shifted. Maybe one possible is because of the solvents we are using. Water as a solvent. Maybe this is a solvent effect or impurity in the solution itself that we need to understand. As you can see, this peak should be compared with this one from other groups work. You can see. So yes, our is a little bit shifted to this 231, and our shifted to higher wavelengths. So again, we tested their geos, graphene oxides, IR spectra. It contains not only carbon triple bond and double bond also, and CO group. So it confirms presence of not only carbon but oxygen. Also, it contains, of course, because it is in it shows that as we did IR spectroscopy of dry powder, but it still shows some portion of the water molecule. Yeah, you can see this is the initially produced graphene oxide. Looks mostly graphite oxide, and we prepared a film, but after preparing initial effort, it came out. You can see it has very low heat resistance, but it came up, it peeled up. But eventually we managed to prepare very very nice film. You can see here these were initial efforts, but now we corrected it, and with our own home built proprietary system, this system could give us now this kind of nice films. Actually, I have been collaborating with Indian scientist who is expert in RGO, and he visited last year is a collaborative work, and we prepared a very nice. This is the films prepared with together with him. So I'm very much thankful to my colleague. And then here I would compare here the XRD of the I presume it's zero, but it appears that this is the XRD spectra of our sample. You can see the mostly look like this is the graphite peak here, and this is the graphite peak with published by Kumar et al. In 2013, and you can see here this the appearance of this peak around 12 2 theta equal to 12 or something like 11 should be compared with this peak, and this peak appearing intense peak of this of our sample shows that hint us that our sample is graphite oxide, not or multi-layer graphene oxide, so several layers. So it's showing property of the graphite oxide, and it also shows few percent of only very few though small of graphite contamination. I mean, it was not leached out completely, and also graphite and then powder, then processed chemically. So there is very small percent of impurity. Maybe this is the cause why we see our sample a bit slightly blackish than the other reported papers, other reported work. And then eventually after that we reduce our graphene oxide solution by various methods. We found that hydrogen was the hydrogen reduction by hydrogen was the best one, and then we tested another alternative method also by only first we prepare a film of the geo by this solution preparing on the glass, and then heated our sample up to, let's say, 500 degrees centigrade. You can see with increasing the temperature of the substrate, the peak of this geo sample slightly shifted, red shifted. It means that it is slightly, it's not completely reduced, but it is partially reduced. So our sample is semi-reduced sample. And also you can see, compare, this is the Raman peak of our sample, and this is the published one. If you see here, if you compare here, this 2D peak and D plus D peak appearance confirms, or in between these two peaks are very much close to this other groups work. Here you can see here they are not resolving very nicely, but I mean you can see the signature. It confirms that we became able to form a geo or semi RGO. And then we tried our best to form a solar cell, putting this geo on perovskite layer that I mentioned here. And this one is copper tape as an electrical contact, because we did not have vacuum deposition. So at the first hand, we wanted to try with this, and actually, indeed, of course, we could not see very nice photocurrent and photovoltaics, but as a signature, when there was no sunlight on top of this, the photocurrent was 0. But once we irradiate the solar radiation, we could see photocurrent of in the nanometer scale, nanoampere scale, and some millivolt scale voltage. For example, after this is a sun simulator that we have, it produces a visible light, and our sample were exposed here. You can see the range of this light. Our sample were here, and once you expose it, you get photocurrent and photovoltage. And we varied the intensity, and after varying the intensity, we could see variation in the current. It means that it is working as a solar cell, but there is severe problem in the, maybe there is a large amount of electrons were lost, maybe in the interface, or recombination because of the large defect in the RGO, or we don't know it, or in the TiO2 itself, or lost, mostly we expect mostly lost in the interface between RGO and the copper, because mostly people do, this is not a good contact. So next step, we will replace this metal stripe with vacuum deposition. So so with this results of, I would like to summarize my talk. We discussed briefly. We discussed mostly optical and structural and electrical properties of transparent films, and also we discussed fabrication of the perovskite layer, and also geo. Mostly we discussed formation of the geo and RGO layers, and then we compare the optical properties, and then we discussed the formation of the perovskite solar cell and their some photovoltaic effect. Actually, we presented after successful test, we prepare several set of small solar cells. You can see here, this is our solar cell, 5 sets of solar cell, and we demonstrated it in a national science day in Nepal. You can see here students are curiously showing, demonstrating. We could see, as I said, nanometer scale, nanoampere scale current, and a few hundred millivolt of voltage. So with these comments, these are the group members. I thank for the TWAS for supporting, and I thank you for your kindly hearing my talk. Thank you so much.
Thank you, sir. Thank you for sharing a wonderful knowledge with us regarding the perovskite solar cell, graphene oxide, and give very fruitful knowledge. Definitely that will help for the researcher. So there's no question in chat box, sir, so that's why I'll continue for next process. So it is our great pleasure to join us, sir. In future also, our institution is ready to invite you, sir. It's a wonderful topic. Thank you, sir. Now, I request dear participants to share online feedback.
Thank you for wonderful, comment on the chat box. I was delighted to have this kind of comments. Thank you so much.
Yes. Very good.
Okay.
Yes, sir. Very good sessions there.
Yeah.
No
Yeah.
doubt.
Can I ask a question?
Dr. David
Hello.
Yes.
want to
Okay.
say something, sir?
Yes.
Okay, sir.
Thank you very much for the nice presentation.
Yeah, thank you, David.
Really, I really enjoyed it. I just wanted to ask, of course, you mentioned that you have used metal ammonium lead triodide as your absorbing layer. And of course, before you mentioned that you highlighted that, normally the band gap of this perovskite layer is, a bit high as compared to the silicon-based solar cells. Is there anything you are doing to, reduce the band gap?
Yes, band gap of the perovskite itself, you mean?
Yes.
Yes. Actually, people. Maybe in the next step, we will mix a fraction of the iodine with bromine, and but also when you mix with bromine or chlorine, its performance decreases. So people are looking other. And now in the meantime, I'm not focusing on this perovskite itself. I'm just following the procedure what other people, other groups work.
Okay.
But now I'm focusing only in the RGO. After this, and for sure, by that time somebody will discover good substitute, or not the bromine or chlorine. Then we'll try. Anyway, thank you so much for your. I think we need a collaboration with theoretician like David.
Yes, that would be interesting. So one more thing, please. One more thing, please.
Maybe we'll be in touch, and please, I will ask your email communication later. So it's very nice.
That would be great. Okay, that's fine. Okay, all the best.
Hello.
Thank you so much.
Thank you so much.
It's really been a very insightful presentation by all of you, all the four speakers, Dr. Poinkar, Dr. Gurnule, David Obada, and Dr. Bhim Kafle also. I just, for this deep-rooted information, what you have been given, but I have one question, Dr. Kafle, if you can answer me. This climate change and pollution is taking a lot of toll on this precious earth. Sir, is it possible that we can look up to nanoscience or nanomaterial to control this kind of pollution over here, sir? Is it possible?
Yes. I mean, scientists are, trying to this. Use this carbon dioxide to sequence it. To reduce the amount of carbon dioxide, even by using zinc oxide film to convert into other useful material, like Professor Gurnule said. It is possible, but it's not 100% realized yet, but scientists are trying to do this. So maybe Professor Gurnule could answer very nicely. Yes, I think there are many work are going on to use this carbon dioxide to reduce. Yes, it is possible.
Yes, true. Thank you very much, sir. In fact, I just wanted to ask this question to Dr. Gurnule also, but I'm not seeing as of now present over here. So I thought I just took an opportunity to question you only.
It's very possible.
Very good information, sir.
In the same kind of Professor Solar cell, there people are trying to use carbon dioxide. So it is possible that you can see many articles on this. I had a interaction with. Yes, I had an interaction with Korean professor. He visited Kathmandu recently, and he showed that zinc oxide film also can absorb this carbon dioxide and convert into other, and decompose it. So there are a lot of work are going on. I think it is possible.
Yeah, you mean to say this technically it is possible. It's just a matter of time and research. Maybe take some time to
exactly. Yes,
to make it possible, isn't it, sir?
Yes, it's government's investment in the research. It determines, yeah, you're right.
Yes. Thank you very much, sir.
Yeah, thank you.
Okay, thank you, sir. Yogita Bodke. Professor Yogita Bodke wanted to say something.
Sorry, if I think I missed. Yeah, pardon me.
Professor Yogita Bodke wanted to share online feedback.
Good afternoon, sir. Good afternoon, all of you. It's a very great opportunity for me to meet Dr. Koinkar from Tokushima University, Japan, Dr. Gurnule sir from Nagpur University, Dr. Obada from Nagpur University, Dr. Kafle from Kathmandu University via the International E-Conference on the Multifunctional Advanced Material organized by the Department of Chemistry, Mahatma Gandhi College, Armory. Dr. Koinkar sir gives the detailed application of an laser technique for the preparation of an nanomaterials and how we can increase the conductivity of the material. Really, it's a new way of an nanoscience, sir. Dr. Gonle sir gives a huge application of an nanomaterials in various fields such as an cement, OLED material, conversion of an CO2. That is the very much good application of today, that we converting the CO2 to carbon nanotubes, etc. So, sir, you are have a very dynamic knowledge about the chemistry. I'm very much thankful to sir. Dr. Obara, the University of Zaria, gives the concept of an electronic base structure and calculation of an electron and hole transfer. So very deep concept we study today, sir. Another dynamic personality that we meet today, that is Dr. Kafia from the Kathmandu University. Sir focuses on the ferroelectric materials and mechanism of an photo generation and gives the preparation of an various film material that is used in the solar plants. And sir also share his research, that is the preparation of an OLED, preparation of an solar plant from the dyes. That's the new concept that I think. So overall, it's a very fruitful session, sir. And I congratulate all the organizers, Dr. Satish Kola, sir, head of the department, so sir, as well as the principal of the Armory College. And I think it's a very big opportunity for the interiors to be to aware about this nanomaterial science and its advances and its application. So I am very much thankful to the organizer to be a part of this today's session, sir. So thank you much. Thank you, sir.
Thank you so much for online feedback. Now I invite Dr. Naresh Banso from Vote of Thanks.
Hello, thank you, Satish sir. Good afternoon to all. It's my privilege to deliver the vote of thanks. First off, I would like to forward my sincere thanks to Dr. Koinkar for their valuable talk on the graphene material. I also would like to show my gratitude towards Dr. Gurnule for delivering such informative talk on multifunctional material, its impact on society. I was fortunate for us to have Dr. Obada because he had elaborated the various density functional material theory. I also would like to mention the magnificent talk by Dr. Kafle on perovskite and solar cell. Thank you very much all the keynote speaker for your valuable guidance. I would like to show my sincere gratitude towards my mentor of this information international conference for principal Dr. L.H. Khalsa. His timely inspiration and guidance has made this event successfully. I wish thank you to the convener of these events, Professor S.M. Sontakke, and Secretary of these events, Dr. Satish Kola, for his supports and guidance of this event. How I can forget the most essential part of this conference, that is our participants from all the corner in country and abroad. Thank you very much to all the participants. And finally, I am thankful to all my colleges who directly and indirectly play a role of bringing this international event with flying colors. I especially thank to Professor Sunil Chute sir and Dheeraj sir for their technical support. We look forward to same in future also. All participants will receive certificate on successful submission of feedback. With the prior permission of principal, I am declaring that today's conference is over. Thank you so much, sir. Take care.